Welcome to your first lesson in trigonometry. This first lesson here is just going to go through some basics that you're probably already familiar with from sort of year 9, 10, and from unit 1, 2. But it's a good refresher and it sort of forms the building blocks of the rest of the chapter. So let's get started. Okay, so the three key concepts we're going to be going through today are first, the trigonometry of right-angled triangles, so SOHCAHTOA. Then we're going to look at radian measure, and then we're going to review our exact values. Okay, so good old SOHCAHTOA. You probably remember this word. I mean, I don't think I'm ever going to forget the word SOHCAHTOA. And if you ask any adult if there's one thing they remember from their maths class, this is probably the word they remember. But if you have some trouble remembering your trig ratios or anything in maths, it's always good to make up a mnemonic, okay? So this is like sort of a saying, so I'll read the middle one. Some old hairy camels are hairier than others are. So this is just a way to remember phrase or a word, some sort of like funny rhyme or whatever. Okay, let's get into the lesson. Okay, so trigonometry is a branch of maths that studies the relationships between side lengths and angles of triangles. Okay, and we're going to first start with a right angle triangle. Okay, now the first thing we need to do is we need to be able to label our triangle correctly. All right, so we've got three different sides. We've got the hypotenuse, which is always the longest side of a right angle triangle, and it's always the one that is opposite the right angle. Okay, so this is our hypotenuse, and I'm a bit lazy, so I'm just going to write HYP there for short. Okay, now we have an adjacent side and an opposite side, and these two sides depend on what we call our reference angle, so the angle we might be talking about in our question. So for example, if this was our reference angle down here, and theta is the Greek symbol that we often use to represent an angle, then the side that is adjacent to that angle theta would be this one here. Adjacent just means beside, okay? And then the side that is opposite to our reference angle would be this side up here, okay? But if my reference angle was this one, okay, that changes my adjacent and opposite side, because now this side here is the one that is beside my reference angle. Okay, and then this one across here is the side that is opposite my reference angle. Okay, the hypotenuse never ever changes. That's always the one that's the longest, that's across from the right angle. Okay, now I've also included Pythagoras theorem. That's probably something that you've used for a long time in your math classes, but here we have c squared equals a squared and b squared. Just important to remember that c squared is referring to the hypotenuse. So once we've labeled our sides, we get these three relationships, okay, between the size of the angle and the lengths of the side of the triangle. So again, you're probably already familiar with these, but just to go through them, what we have here is that the sine of theta, whatever the angle size is equal to the length of the opposite side divided by the length of the hypotenuse. Okay, similarly, we have cosine of theta is equal to the adjacent over the hypotenuse, and tangent of theta is equal to the opposite over the adjacent. So that's where we get our SOHCAHTOA, okay? If you can see here, sine is opposite over hypotenuse, that's the SOH. Cos is adjacent over hypotenuse, that's our CAH. And tan is the opposite over the adjacent, that's our TOA. Okay, so that's where we get the word SOHCAHTOA from. Now, it's really important to just remember that this only works when we have a right angle triangle. Okay, you can't use these relationships when you have different types of triangles that don't have a right angle. Okay, so let's jump into a couple of examples where we're going to use our trig ratios, SOHCAHTOA, to find a missing sort of side length or an angle. So the first question says, for triangle ABC below, if angle B is 40 degrees, so that's important, I'm going to underline it, angle B is 40 degrees, and AB is 5 centimeters, so that's that length is 5 centimeters. What's the length of side BC? Okay, so let's like label things here. So first I'm told angle B is 40 degrees, so that's my 40 degrees there, and then I'm told AB is 5. I'm going to just leave the units off. For now, we'll put some units in at the end. And I want to calculate the length of side BC. So I can see BC here. That is my hypotenuse. So I'm going to label it H. Now my reference angle in this case is that 40 degrees. okay? So what I've got here is I need to find out the hypotenuse, and I've been given this side here, which is the adjacent side, okay? So I want to use the trig ratio that involves the adjacent side and the hypotenuse. And so if I look at my ratios over here, that's cosine. So I'm always going to start my working out by just writing down the formula, okay? So the cos of theta is equal to a over h, and then I'm going to fill in the things that I know. So theta in this case is 40 degrees, so cos of 40 degrees is equal to the adjacent side over the hypotenuse, okay? Now you can put that straight into your calculator and solve for h, but let's just do a little bit of rearranging of that for fun by hand first. Okay, so to solve for h, I would first multiply both sides by h to get h cos of 40 is 5, and then I would divide both sides by the cos of 40. Okay, and then I'm going to use my calculator to work out the value of h. Now it's very important to remember to check your calculator whenever you're working with angles to make sure you're working in either degrees or radians. Okay, so we're going to add a calculator here, and then if I go up to the top here, you can see it says RAD. That means my calculator's in radians. So this question's degrees, and you just have to click on it and it will change to degrees. Okay, so it's a really quick way to change between radians and degrees. Okay, and if you wanted to get back to radians, you just click on it again. All right, we're working in degrees here. So we're just going to put in our calculator here, 5 divided by the cos of 40. So 5 over. And your trig functions are this button here, so you can see all of them. So cos 40, and we hit enter, and we get 6.527 and so on. So we could just round our answer to 2 decimal places. So h would be equal to 6.53. Okay, let's try another example. So this time we have AC, the length AC being 3 centimeters. Okay, and then AB is 5 centimeters. And we want to calculate angle C. So we want to calculate this angle here. Okay, so first let's label our sides. So the angle we want to find out is this one. That's our reference angle. So that means that this 5 here is the opposite side. Okay, and the 3 is the adjacent side. So the ratio that uses the opposite and the adjacent would be this one here, tan. Okay, so let's write that down. Tan of theta is opposite over adjacent. And then let's fill in what we know. So theta in this case is angle C. Opposite was 5, and adjacent is 3. Now to solve for an angle, we need to use the inverse trig ratio, okay? And the way we'll write that is like this. So C is equal to the inverse tan, okay, of 5 over 3. All right, and then we can put that straight into our calculators to work out angle C. Okay, so we can go into our trig functions again here, and you can see the inverse tan is down on the bottom row. And then we can just put 5 over 3 or 5 divided by 3 and press enter. Okay, and we get 59, about 59 degrees rounded as angle C. Okay, and that's it. Okay, so the second key concept that we're going to review is looking at radians, okay? So radians are just another way to measure angles. We're used to degrees, but radians is another way. It's sort of just like with weather, you know how you can have Celsius, degrees Celsius, or if you're in the United States, you would measure it in degrees Fahrenheit. It's just 2 different ways to measure the same thing. Same with centimeters to inches and that sort of thing. So in methods and in most math courses, you're actually going to be working in radians most of the time, okay? And there's lots of reasons for this that I won't go into, but there's a nice like sort of relationship between radian measure and sort of angles and sine and cos and tan and all these things. Okay, we're going to discover some of them as we go along this chapter. Now, a radian is defined as the angle, okay, that is subtended at the center of a circle by an arc that is equal in length to the radius of the circle. Okay, like what does that mean? All that means is basically this angle here, I'm just going to say this diagram is like not to scale, but what we're saying here is the angle that's made by the length, where the length of this arc is equal to the radius of the circle, okay, that angle there is 1 radian, Okay, now when we want to think about converting between radians and degrees, we can use our knowledge of circumference of a circle to kind of understand this. Now, hopefully you remember that the circumference of a circle is 2 pi times a radius, right? So the circumference of a circle is always 2 pi times whatever the radius is. So 2 pi times bigger than the radius. What that means is we could actually fit in, if I put in like another sort of radius here and here and here, we would fit in just over 6. We'd be able to fit in 6 sort of like arcs all the way around the circle. So what that means is 2 pi radians, okay, 2 pi radians is equal to 1 full circle, which we know is 360 degrees. So that's where our conversion comes from. And typically we simplify that to say that pi radians are equal to 180 degrees. Okay, so that's the conversion rate between radians and degrees. Okay, so we do need to get used to working in radians. Basically for the rest of this chapter, I'm only going to be working in radians. Okay, so it's very useful to know some common equivalent angles between degrees and radians because you're probably very, very comfortable and used to degrees, and we need to be able to quickly sometimes or just easily convert to radian measure. So we'll start with what we know, which is 180 degrees is pi radians, okay? Now, if I say, okay, what's 90 degrees then? Well, then that's going to be half, right? So that would be pi over 2 radians, okay? If I start with 180 degrees and I look at 60 degrees, well, 60 degrees is a third of 180 degrees. So I would get that 60 degrees is equivalent to pi on 3 radians. Okay, similarly, I can do 45 degrees. That's a quarter of 180. So 45 degrees is pi on 4 radians, and 30 degrees is pi on 6 radians. Okay, looking at some other common ones here, I'll do 360 first because that's nice and easy. We already talked about that. 360 degrees is 2 pi radians. And then 270 degrees is 1.5 times 180. So we would write that as 3 pi on 2, right? Because 3 over 2 is 1.5. Okay, if you've got some trickier sort of degrees to radians, we've got a formula for you, and it's just that if you're going from radians to degrees, you're going to multiply by 180. Oh, we're missing a degree sign. 180 degrees over pi, and if I'm going from degrees to radians, we're going to multiply by pi over 180 degrees. And I'm going to show you how you can remember which one is which because I think it's kind of easy to mix those up. All right. Okay, if I want to convert 300 degrees to radians and I don't have a calculator, all right, I'm going to start by writing down 300 degrees. Now I know I've got to multiply it by either pi on 180 or 180 on pi. And the reason that I know that it's pi over 180 degrees is because I want my final answer to have a pi in it, and I want my degree signs to cancel out. Okay, so I never really try and memorize things in maths like that. I always just try and think about what is the logical way to get to my answer. Okay, so 300 times pi over 180 is just this. And then, of course, we're going to simplify that to get like the simplest fraction possible. So I would start by going, oh, well, both of those can be divided by 10, so 30 pi over 18. And then I can easily see that 30 and 18 can be divided by 6, okay, which gives me 5 pi over 3. Okay, so 300 degrees is equal to 5 pi on 3 radians. Okay, the last section we're going to do in our trig review here is looking at exact values for some of our angles. Okay, now I'm going to show you the way that I was taught in school, and I always go back and do this when I'm like not sure about my angles. You do need to know these that I'm going to show you, okay? So hopefully these triangles help you out. If not, I'm going to direct you to a YouTube video that you might find a little bit better. First of all, we want to find the exact values for pi on 4 radians. So we start by drawing a right isosceles triangle, okay? So I've got a right angle triangle there. It's isosceles, which means my two sides are the same, okay? And the two shortest sides have a length of 1 unit. And then by Pythagoras theorem, the hypotenuse would be the square root of 2. Now, because it's an isosceles triangle, these angles here are the same, and they're both 45 degrees, or pi on 4 radians. Okay, so because I've got a right angle triangle, I can now use SOHCAHTOA to find out the exact value of the sine, cos, and tan of pi on 4 radians. Okay, so the sine of pi on 4 would be the opposite, which is 1, over the hypotenuse, which is root 2. Okay, so that's our exact value for the sine of pi on 4. You'll often see this written as root 2 on 2 because we don't like having a square root sign in the denominator. It's not like good mathematical, let's say, grammar, okay, or notation. But either of those are both equivalent, okay? This is just with the denominator rationalized. Similarly, we can find the cos of pi on 4. Okay, so again, the cos of pi on 4 is the adjacent, and in this case, the adjacent is also 1. And the hypotenuse is root 2. So they actually have the same value, okay? The sine of pi on 4 and the cos of pi on 4 are both 1 over root 2 or root 2 over 2. The tan of pi on 4 is opposite over adjacent, so that would be 1 over 1 or just 1, okay? So the value of the tan of pi on 4 radians is 1. Okay, I've put in here, it often comes up in the sort of exam reports that students don't know these exact values. You have to know this for paper 1, okay? You're definitely going to be examined on it at some point within that paper. Okay, we can do a similar type of thing to find the exact values for pi on 6, which is 30 degrees, and pi on 3, which is 60 degrees. What I do here, or what is helpful, is if you start with an equilateral triangle that has a side length of 2 units. So each of those sides is 2. From here, what I'm going to do is I'm going to cut that triangle in half to make a right angle triangle for myself. Okay? So if I cut that triangle in half, that means that this length here is 1, and this length here is root 3. Okay? If I use Pythagoras theorem. Now, I'm going to just erase the rest of that triangle just to make it nice and clear for us. Okay, so let's look at the angles in that triangle. If this was an equilateral triangle, then that angle there was 60 degrees, okay, or pi on 3 radians. And this angle here would be half of 60, so 30 degrees, or pi on 6 radians. So from here, I can now find the sine, cos, and tan of pi on 6 and pi on 3, okay? And if you want to test yourself, see if you've got these already memorized, maybe you could try writing them down and then compare your answers with mine. So let's start with the sine of pi on 6. That is the opposite, which would be 1, over the hypotenuse, which is 2, so a half. The cos of pi on 6. So if I'm looking, there's pi on 6, the adjacent side is now root 3, and hypotenuse is 2. And the tan of pi on 6, okay, that would be equal to the opposite over the adjacent. The opposite is 1, the adjacent is root 3, and again, you'll often see this written as root 3 over 3, okay? And we'll do the same thing for pi on 3 radians. Okay, and so we end up with these relationships here. So we get the sine of pi on 3 is 3 over 2, the cos of pi on 3 is a half, and the tan of pi on 3 is root 3. So if you can sort of get yourself to understand where those triangles come from, you never really have to memorize these values. You can always sort of just sketch out your triangles. That's sort of what I do when I'm like working through an exam. I always go back to sketching the triangles just to make sure that I've got them right and my memory hasn't messed up. But you might be really good at memorizing things, and hopefully throughout the course you'll get to know these values very, very well. So I have summarized these for you in a table, and I've added in the 0 degrees and 90 degrees. So you can see the first 2 rows of this table just show you the angles in degrees and in radians, and then you've got, so for example in this column here, we've got like the sine of 0 degrees or 0 radians is 0, the cos of 0 is 1, and the tan of 0 is 0. And so on, okay? So it might be handy for you to refer to that as we go through some of the questions. Okay, I've also included a YouTube video. I know that my students really liked this video for a way to remember the exact values of the angles. So you're welcome to have a look at that video and see if you prefer that to my triangle explanation. Okay, so we're going to use our knowledge of exact values to answer some questions. So the first one just says, what is the exact value of tan of pi on 4? And if I was in a test and I couldn't remember, I would quickly go, okay, pi on 4, that's my isosceles right triangle. It had side lengths of 1, so I know the hypotenuse is root 2. If I'm looking for the tan of that angle, I'm doing opposite over adjacent, O over A, which is equal to 1. So that concludes our sort of review of the trig basics. We're going to move on in the next lessons to have a look at the unit circle, and then we're going to start applying these things to do things like solve trig equations and sketch trig graphs, all fun things. All right, guys, a little math joke for you. Is that 1 pi or is that 2 pi? If you're a math person, you know what I'm saying. This lesson is going to be a review of the unit circle. You were introduced to the unit circle in Unit 2 in methods, but if you're like most of my students, a refresher on this is probably a good thing to have, okay? I'm going to try and explain it as explicitly as I can, so like buckle in and let's get started. All right, so we're going to touch on 3 sort of key concepts that we're going to look at how we measure angles in the unit circle, and then we're going to define sine and cosine, which are pretty similar, and then we're going to have a look at tangent on its own. Okay, so the unit circle is just a circle that is centered at the origin, okay, on a coordinate plane, and the axes cut that circle into 4 quadrants, okay? The radius of a unit circle is 1, that's why we call it a unit circle. So it sort of looks like what we have here. So quadrant 1 is the quadrant where sort of all of our x and y coordinates would be positive, and then we label the quadrants in an anti-clockwise direction. Okay, as you can see in the diagram in front of us. Okay, so we're going to start by looking at how we label angles on the unit circle. So the first thing to note is that we always start from the positive x-axis. So this would be what we call 0 degrees, okay? 0 degrees, or of course, we're working in radians. That little C sign is a radian symbol. 0 radians, okay? Now we measure our angles in a anti-clockwise direction starting from that axis. So if I drew in say a line here, I could measure that angle. Looks like it's probably about 40, 45 degrees, okay? Now let's kind of look at our main angles around the unit circle. So if I drew an angle all the way over to the y-axis, that would be, hopefully you can see, a right angle, okay, 90 degrees, or pi on 2 radians. I'm just going to work in radians now, okay? We're going to sort of not forget about degrees, but kind of forget about degrees. Okay, now if I kept going around this unit circle, I'd get all the way to a straight line, okay? We know it's 180 degrees, or pi radians, okay? Keep going. This whole angle, so starting at the x-axis and kind of going 3/4 of the way around, would be 3 pi on 2 radians. And then I could do a whole rotation, which would be 2 pi radians, okay? So that angle on the x-axis is 0 or 2 pi, and we can actually continually loop around the unit circle. So I could draw, I'm just going to erase some of my markings here. Okay, so I could actually draw something like this and say, okay, this angle here, do you see how it sort of spirals around? That's actually now 2.5 pi. So we could write that, we usually write that as an improper fraction. Okay, 5 pi on 2 radians. And then we would have, over here, we would have another pi on 2 radians. So this could also be 3 pi, and so on and so on. And you could go around it infinitely, okay, forever. You could loop around forever, okay? So you can see here that you've got lots of angles that are sort of equivalent to each other, and that's going to help us out a little bit later in the lesson. Now we can also measure negative angles on the unit circle. So we start at x, or at the x-axis again, but this time we're going to move in a clockwise direction. So this angle here would also be negative pi on 2 radians, okay, like negative 90 degrees. Okay, this would be negative pi, this would be negative 3 pi on 2, this would be negative 2 pi, and so on forever and ever and ever. Okay? Okay, so for this example, what we're going to do is we're just going to draw these angles on the unit circle, okay? So the first one we have there is 3 pi on 2, so 3/4 pi. So it kind of helps to think about breaking these angles up. So I know that 3 pi on 4 is the same as 2 pi on 4 plus 1 pi on 4. And the reason I've done that is because I know 2 pi on 4, that's actually pi on 2, isn't it? Okay, so I know that 3 pi on 4 would have to be pi on 2, which gets me to here, plus another quarter. So it would be somewhere in that second quadrant. Okay, so this angle here is our 3 pi on 4. All right, and I'll do the other angles in different colors just so we don't get confused on our diagram. So let's look at this second angle here. We've got negative 2 pi on 3. So like you're thinking negative 2/3, okay? So we know that negative 1/3 would have to be somewhere sort of like here, right? It's like 60 degrees. And then if I do another negative 1/3, okay, I'm going to get somewhere in that third quadrant down here. Okay, so what I've got to be thinking here is I could split this up into negative 1/3 minus another third. I know that's bigger than a half, okay, but less than 1. So it's got to be somewhere in that third quadrant. Okay, so what about the next one there? We've got 5 pi on 2 radians. Okay, so 5 over 2, that's like 2.5. Okay, so I can rewrite that as 2 pi plus another half a pi. So I know that 2 pi is 1 full rotation plus I need another half. So that green angle there, that represents my 5 pi over 2 radians. So next we're going to have a look at how we can use the unit circle to define sine and cosine. Okay, so remember the unit circle is just a circle with a radius 1 centered at the origin. Now, if I just pick any point P, okay, like an arbitrary point P on this circle, it's going to have coordinates x, y. And I'm just going to look in that first quadrant there for now. So x and y are positive. Okay, now that's my radius, right? So my radius there is 1, okay, because it's a unit circle. And if I sort of draw in this right angle triangle here, I know the height of that triangle would have to be y, okay, because it's going up to that y coordinate. And the length of that triangle there, the base would be x. Now, if I think about my SOHCAHTOA here, because I've got a right angle triangle, okay? If I wanted to say, like, what is the sine of theta? Well, I know the sine of theta is the opposite over the hypotenuse. So the opposite in this case is y, right? That's the side opposite to theta. And the hypotenuse in this case is 1. We know that it's a measure of 1 because it's a unit circle. Okay, so that's where I get this relationship that the sine of theta is equal to y. It's equal to the y coordinate, okay? And that's like the definition of sine all the time, right? So whatever the sine of, whatever that angle is, so if it was like the sine of 50, if you put the sine of 50 into your calculator, it would be equal to the y coordinate where that angle, you know, is subtended by the radius, okay? Similarly, we can define cosine, okay? So the cosine of theta, remember, is adjacent over hypotenuse. So the adjacent in this case is x over 1. So we get this relationship that x is equal to the cosine of theta. Okay, so now knowing this relationship, right, that x is equal to the cos of theta and y is equal to the sine of theta, we can start to expand and use our knowledge of exact values to find the values of some other common angles. Okay, let's see how we would do this. Now, we're going to start first by looking at the angle 0 radians, and that would just be that line there. Remember, we started on the x-axis with 0, okay? Now, because we've got a unit circle here, that is the point 1, 0. Okay? So if I wrote that in terms of cos and sine, remember that the cos of theta, so this in this case here, theta is 0. So the cos of 0, sine of 0. So what that's telling me then is that the cos of 0 is equal to 1. Okay, so the cos of 0 is 1. And now I know that the sine of 0 is 0, right? Because the sine of theta is equal to the y value. So the sine of theta is 0. Okay. Similarly, let's do all of our sort of multiples of pi on 2. So if I look at pi on 2, that angle there, that's the point. What point is that? 0. The x-coordinate is 0. The y-coordinate is 1. Okay. So what that's telling me is that the cos of pi on 2 is 0. Okay. The cos of pi on 2 is 0 because the x-coordinate there is 0. And the sine of pi on 2 is 1. Okay. Because the y-coordinate is 1. All right. You might be able to go through and work out the rest on your own. Otherwise, you can sort of watch me do it. Okay. If we have a look here, that point, okay, so now I'm at pi radians. Okay, that is the point. The x value there would be -1, y would be 0. So that means that the cos of pi, because remember this angle here is pi. So the cos of pi is -1. That's the x value. And the sine of pi is 0. Okay, so isn't this fun? All right. So our next one here would be this point down here. So our angle down here, remember, is 3 pi on 2. And that is the point 0, -1. Okay, so the cos of 3 pi on 2 is 0. And the sine of 3 pi on 2 is -1. And that's going to really help us out sort of later on, especially when it comes to understanding where the graph of sine and cosine come from. Okay, if we kept going around the circle, we'd get back to 2 pi here. So look at that. That means that the cos of 2 pi is actually equal to the cos of 0, okay, which is 1. And the sine of 2 pi is the same as the sine of 0, okay? So if you put sine of 2 pi into your calculator and sine of 0 in your calculator, you'll get the answer 0. You get the value 0. Okay, they're the same. They're equivalent angles. Okay, so we're going to use this knowledge now to evaluate a few more angles. So if I want to work out the cos of 5 pi on 2, first of all, let's find out where is 5 pi on 2 on my unit circle on my diagram. So I don't actually have to draw the circle in, but what I can do is go around to 5 pi on 2. So remember 5 pi on 2, that's just 2 pi plus another half a pi, okay? So 2 pi would be here, half a pi would be there. Now, on the unit circle, right, that was, if I drew in my circle, okay, that's the point 0, 1. Okay, remember the cos of theta is equal to whatever the x-coordinate is there. So that means the cos of 5 pi on 2 would be equal to that x-coordinate, which is 0. Okay, let's try another one. This time, let's look at a negative angle. And this is a big one, -9 pi. Okay, let's try and count in 2 pi's. Okay, so -9 pi would be going this way, right? If I went like this, that would be -2 pi, one sort of loop around, -4 pi. Oh, this is going to be a big spiral. -6 pi, -8 pi. And now to get to 9, I just need to go around to here, okay? So basically what that's saying is the sine of -9 pi is just going to be equal to the y value at that point, okay? And it's the same as saying, like, if you recognize that, that's the same as the sine of pi, okay? It's going to be the same value. So on my unit circle there, remember sine is equal to the y-coordinate. The y-coordinate at that point would be 0. Okay, so the sine of pi is just 0. Okay, so we're going to have a look at how we can use the unit circle to define the tangent angle. And we're going to look first at the geometric definition, okay? And that is that the tan of an angle is the length of a segment that is tangent to the unit circle, okay? So remember, a tangent is a line that just touches, say, the circle at one point. So that's where the word tangent comes from, okay? Or the trig ratio tangent. So that's just basically saying here, if I just let's just look at this first angle here, okay? Whatever angle that is there, the tan of theta is equal to the length of that segment that is tangent to the circle. okay? As theta gets bigger, okay, so now if we were looking at that angle there, then the tan of theta would be this, this whole length of that segment. And I've included an extra sort of link for you to go and have a look at, because there's a really nice sort of applet that you can play with the different like angles and lengths of the line to really get an understanding of what I'm looking at. Okay, so another way we could sort of like look at this or find our definition of tangent here is, now if we're taking, like we've said, this length here is the tan of theta, and we're going to use ratios of the sides of similar triangles to get our definition here. So if we look at the length of BC over OB, okay, so that base there, that would be equal to the length of AP over OA, which would just be that short bottom of that triangle there, that right angle triangle. So let's fill in some things here. BC is actually the tan of theta, okay? That's how we've defined it. And OB is 1, okay? Because that's just the radius of the circle. Okay? So that's equal to AP. And remember, P is any point XY. So AP would be just the height of that triangle, which is Y. Okay, and OA would be the base of that triangle, which is X. So what we end up with here is that the tan of theta is equal to Y over X. And what you might remember is that Y is the sine of theta, and X is the cos of theta. So we get this nice relationship relating sine, cos, and tan, okay? That the tan of any angle is equal to the sine of that angle divided by the cosine of that angle. So we can use this relationship that the tan of theta is equal to sine theta over cos theta to now evaluate the tan of the angles that we know. Okay, so if we know that sine is 0 and cos is 1, okay, tan is sine over cos, so 0 over 1, which is 0. Okay, so let's see what happens when we try and work out the tan of pi on 2 radians. So if I try to do sine divided by cos, 1 divided by 0, I can't do that. I can't divide by 0. So tan of pi on 2 radians is actually undefined. The tan of pi radians would be 0 divided by -1, so 0. The tan of 3 pi on 2 can't divide by 0. It's also undefined. Okay, and then the tan of 2 pi would be 0 divided by 1, which is also 0. Okay, so now we can use a little bit of that knowledge to evaluate some angles in terms of tangent. Okay, so if we want to find the tan of -3 pi, first let's draw that in. We know that this would be -2 pi, this would be -3 pi. Okay, so that's the same as the angle pi. Okay, so the tan of -3 pi is equal to the tan of pi. And if we remember, the tan is sine over cos, or y over x. Okay, so for this point here, we would have -1, 0. Y over x would be 0 over -1, so that's equal to 0. All right, guys, so that wraps up our introduction to the unit circle. Okay, you've got the sort of the summary of the notes there. In our next video, we're just going to expand on the unit circle. We're going to look at some of the really nice symmetry properties that we get within that circle. Okay, guys, another little math joke to get you in the mood for this next lesson. Where are the mathematicians buried? In the symmetry. Okay, today's lesson is going to be dealing with a lot of symmetry, so let's get started. Okay, for this lesson, we're going to be looking at the unit circle in depth, and we're going to be exploring all kinds of different sort of symmetry and relationships within that circle. So for the first part of this lesson, we're going to be looking at the signs of the circular functions, or the trig ratios, sine, cos, and tan. And by sine, I mean, is it positive value or negative value? And then we're going to apply the same thing to negative angles. Okay, so to get started today, we're going to have a look at sine, cos, and tan in the different quadrants, okay? So we start off in quadrant 1, right? This is where any point on the circle that is sort of between the 0 and pi on 2, we're going to have a positive value for x and y, right? X would be a positive value, and Y would be a positive value. So that means that the cos of any angle in this quadrant and the sine of any angle in this quadrant would also be positive. So for example, if this angle here was pi on 3 radians, and we put that in our calculator, cos of pi on 3, that's going to give us a positive value. Okay, so that's what I mean here. Now, by extension, because we know that the tan of theta is sine divided by cos, the tan of theta would also have to be a positive value, right? Because you would have a positive divided by a positive, so tan is also positive, okay? So the first kind of understanding here is that for any angle in quadrant 1, the cos of that angle, the sine of that angle, and the tan of that angle give you a positive value. If you don't believe me, you can go and play around on your calculator for a bit, but just trust me on this one. All right, let's look at what happens to the signs of these trig ratios in the second quadrant. So if I take point P and I reflect it in the y-axis, okay, I would get another point over here, right? And this would basically be the same point, except it would be the negative, whatever the x value was, it would be the negative, right? I've reflected, I'm now in the negative x-axis, but y would still be positive, okay? So what that means that is if I had, so this angle here, okay, if this angle was the cos of theta, this one here, okay, is pi, remember, minus whatever theta was. Okay, so that whole angle there is pi minus theta. Okay, so we could say here that this is going to be the negative cos of theta, but the positive sine of theta because of that reflection. Or we could write this another way. We could refer to that angle, instead of just the negative of cos theta, we could call it the cos of pi minus theta. And what we get here is that it's equal to the negative of whatever the cos of theta is. Okay? Similarly, all right, we can say that the sine of pi minus theta, do you see how sine, like the y value, stays positive in that quadrant? Okay, so the sine of pi minus theta is going to be the same, basically it's equal to the sine of theta, okay? And kind of what that means with like numbers is that if you had, I'm going to work in degrees because it's just a bit easier to kind of explain. If theta was 30 degrees, that's saying that the sine of 150 degrees is equal to the sine of 30 degrees, okay? Now, if I think about tan, remember, tan is equal to sine divided by cos. Okay, so in this quadrant here, any angle in this quadrant, in quadrant 2, is pi minus theta. Tan is going to have to be negative, okay, because it's sine, which is positive, divided by cosine, which is negative, okay? So we get this relationship here. Okay, so we're starting to see some sort of relationships between angles and their values, okay? And what's interesting here is that in quadrant 1, all three, sine, cos, and tan, are always going to be positive, okay? But in quadrant 2, only sine is positive. The value of cos and tan for any angle between pi on 2 and pi radians is going to be negative. Now, let's extend that and have a look at quadrant 3. So this would be reflecting our point P in the y-axis and then in the x-axis. So we would get like sort of a similar point, you know, down in that third quadrant. So if we think about it, x and y are both negative in that quadrant, right? The value of x and y. So this will be the point negative x, negative y, or we could say it as negative cos theta, negative sine theta. All right? But that angle could be also thought about, okay? So this little bit here is theta. So that whole angle there is actually the angle pi plus theta, all right? And again, we can look at our relationships like we did last time. We could say, okay, if I'm looking at the cos of pi plus theta, that's got to be equal to the negative of cos theta, all right? And if I'm looking at the sine of pi plus theta, that's got to be equal to the negative of sine theta. Oops, sorry, that should be theta up there, not pi. Okay. And then if I look at tan in that quadrant, remember tan is sine divided by cos. So if I've got a negative value divided by another negative value, tan is actually going to be positive. Okay, so the tan of pi plus theta is equal to the tan of theta. So in quadrant 3, okay, I get that cos and sine, the value of cos and sine are going to be negative, but the value of tan of any angle in that quadrant is going to be positive. Okay, finally, we're going to look now in quadrant 4. So if I reflect my point P here, okay, I'll draw in my angle. That little bit there is theta. Okay, now this is going to be a point where x is positive, but y is negative. Okay, so we're going to say like the cos of theta is positive, but we have the negative of sine theta. Okay, but if we think of that angle another way, like we've been doing, if we measure that angle from the x-axis, that is the angle 2 pi minus theta. So let's look at our relationships again, and I'll just write them up here. So if I look at cos of 2 pi minus theta, that's going to be equal to the cos of theta. It's going to be a positive value, the same value as cos theta. But if I look at sine of 2 pi minus theta, sine is negative in that quadrant, okay? And then similarly, I can, like I've been doing, I can look at the tan of 2 pi minus theta. And because I get a negative divided by a positive, it's going to be negative. Okay, so in that quadrant, I only get, so for any angle that is between 3 pi on 2 and 2 pi, so that's in this quadrant here, quadrant 4, okay, I get that the value of a cos of that angle is going to be positive, but the value of the sine and tan of that, whatever that angle is in that quadrant, is going to be negative. Okay, we're going to look at some examples with numbers and it'll become a little bit more clear, okay? But that's just where these relationships come from. Okay, so let's sort of review this, all right? You have to know this for your exam and for paper 1, okay? So if we look in quadrant 1, what we can say is that cos, sine, and tan are all positive, okay? In quadrant 2, we get those relationships, quadrant 3, and quadrant 4. So this is sort of like a nice summary sheet for you of all those relationships. Now, that's a lot to kind of try and memorize, okay? There's a really nice mnemonic for us to remember which one is positive and which one is negative in each of the quadrants. Okay, so having a look here, like we said, quadrant 1, they're all positive, okay? So I'm just going to put a big letter A. And in quadrant 2, only sine is positive. So I'm going to put a big letter S, okay? And that's how many sine is positive, the other two are negative. In quadrant 3, only tan is positive. And in quadrant 4, only cosine is positive. Okay, so a lot of people use like a mnemonic. One that we use frequently is all students take calculus. Okay, so you can remember to label your quadrants in that order, starting from quadrant 1, A, S, T, C, to help you remember which trig ratio is positive in which quadrant. Okay, so let's see how we're actually going to use this with some actual angles here. Okay, so this says evaluate each of the following. Now you are going to need to know your exact values that we did in the very first lesson of this chapter. Okay, so make sure you know your exact values for those angles, you know, pi on 3, pi on 6, pi on 4, pi on 2, and so on. So let's have a look. So we want to evaluate the sine of 4 pi on 3. Okay, the first thing we kind of want to do here is identify a reference angle. So what that means is, like, how far away is that angle from either of the x-axes? So I'm going to draw in my coordinate axis here. Okay, so the sine of 4 pi on 3, I'm going to break that into, that's the same as the sine of 3 pi on 3, which is pi, plus pi on 3. Okay, so when I talk about a reference angle, I'm talking about this angle here, okay? And what I mean is, if I look at 4 pi on 3, remember it's pi plus pi on 3. It's going to be down in this quadrant here, okay? My reference angle is always that acute angle that I can make with the x-axis, All right, so I know then that in that quadrant, if I use my all students take calculus, that only tangent is positive in that quadrant. So that means that sine has to be negative. So that's actually equal to the negative sine of my reference angle. Okay, now the reason I need my reference angle is because I know from my exact values that the sine of pi on 3 is root 3 on 2. So this is going to be equal to the negative of root 3 on 2. Okay, let's do another example. So I want to work out the cos of 9 pi plus 4. Okay, so again, I'm going to try and work out my sort of reference angle here. So I can break this into the cos of, I've got 9 pi and 4. Okay, that's like 8 pi on 4 plus pi on 4. Okay, and I know 8 pi on 4 is 2 pi. Okay, and I can do that to work out which quadrant my angle is in. We practiced that in the last lesson. So if I have a look here, 2 pi plus pi on 4 would be here. 2 pi plus another pi on 4. Okay, so my reference angle here is pi on 4. So all students take calculus. Okay, in this quadrant here, all of my values are positive. So this is going to be equal to just the positive value of cos of my reference angle, or the cos of pi on 4. And then I know from my exact values that the cos of pi on 4 is 1 over root 2 or root 2 over 2. Okay, so we've got to work out which quadrant our angle is in, and that will tell you if the value of it is positive or negative. Okay, and then you can work out the actual value of it thinking about your exact values. All right, let's try one more. Let's try with tangent. So I've got the tan of 11 pi on 6. Now, that's just a bit less than 2 pi, isn't it? It's actually, 2 pi would be 12 pi on 6. So it's 2 pi minus pi on 6. So if I draw that angle in, 2 pi minus pi on 6 is going to be just less than 2 pi. Okay, so my reference angle in this case is pi on 6. So, ASTC, I know that the angle's in the fourth quadrant, okay, and I'm looking at tan. So tan is negative in that quadrant. So I'm looking for the negative value of tan of pi on 6. Okay, now I need to know that the exact value of tan of pi on 6 is root 3 on 3. Okay, so that's going to be equal to the negative of root 3 on 3. Okay, I'm going to take you through another type of example that comes up. It looks like a little bit strange, but it's actually a little bit easier, this example. So this is telling us if the sine of theta is 0.4. Okay, we don't know what theta is, but we know that the sine of theta is 0.4. What's the value of the sine of pi minus theta? So again, what quadrant is pi minus theta in? So let's take a look. Pi minus theta would be in that quadrant there, right? If that's theta, this would be pi minus theta. Okay, so ASTC. So in that quadrant, so pi minus theta is in the second quadrant, sine is positive. So this is equal to the sine of theta. And if the sine of theta is equal to 0.4, that's also equal to 0.4. Okay, similarly, let's look at part B. Now we've got the sine of pi plus theta. So what quadrant is that in? So this would be pi plus another theta would be down here. Okay, so this whole thing here would be pi plus theta, that angle there. So that's in my third quadrant. And again, if I label ASTC, I know that only tangent is positive in that quadrant. So that's got to be equal to a negative value of sine theta. Okay, so the negative of sine theta would just be now negative 0.4. Okay, so in this last section, we're going to take a quick look at negative angles, and we're going to sort of define these in the same way that we did in the beginning, okay? So if I take a look now, and I can rename this angle as negative theta, right? Because if I go in a clockwise direction from the x-axis, I've got my negative angles here, okay? So if I'm looking at the negative of theta, I'm just looking at a reflection in the x-axis, okay? So remember, this was my x value and this was my y value. So if I reflect that, my x value stays the same, but my y value is now negative, okay? So what this tells me is that, okay, this is the cos of negative theta. It's actually equal to just the cos of theta, which is this relationship here. Okay, so those two are equal. But if I look at the sine of negative theta, okay, that's equal to the negative of sine theta, because that point, that y value is reflected and it's now negative y. Okay, so I get that the sine of negative theta is equal to the negative of sine theta. Okay, and then similarly, if I'm looking at tangent, I can just look at the relationship between sine and cos. So the tan of a negative angle is equal to negative sine over cos. So it would be equal to, oh, we're missing an equal sign. I'll just add that in, equal to negative tan theta. Okay. So let's look at how we can use those relationships to evaluate a negative angle. So if tan of x is equal to 0.8, what's the value of tan of negative x? So we know from our relationship that tan of negative x is equal to the negative of tan x, which just means if tan x is 0.8, then this is equal to negative 0.8. Okay, guys, so that wraps up our summary here. Remember, you do need to know these exact values, okay? I can't stress that enough. You're going to need to know these exact values, and you're going to have to be able to use this ASTC, these quadrants, to evaluate whether or not an angle is positive or negative throughout the course, okay? We are going to look at a couple of more symmetry properties of the unit circle in our next lesson. Okay, so after our last few lessons, you might be asking yourself, when will we ever use the unit circle? Well, it might interest you to know that sort of trigonometry and circles date all the way back to ancient Egyptians and Babylonians, and they used trigonometry a lot in astronomy to organize the constellations. But actually, you'll probably never use the unit circle for that. You're going to be using the unit circle to do really fun things in methods like solve trig equations. So let's look at a few more properties of the unit circle so that we can do that. So in this lesson, we're going to look at a few more relationships that are found between the sine and cosine of angles that we can explain using the unit circle. So we have two key topics in this lesson. We're going to look first at complementary angles, and then we're going to be looking at the Pythagorean identity. Okay, so the first thing that we're going to look at is the relationship between complementary angles. So what is a complementary angle? First of all, it's just complementary angles are angles that add to 90 degrees or pi onto radians, okay? So let's have a look at our unit circle again. And what we're going to do for this, to investigate these complementary angles, is we're going to have a look at reflecting our point P. We're going to reflect it now in the line y equals x. So the line y equals x is this as a straight line that goes through sort of at a perfect 45-degree angle there. So there's my line y equals x. So if I reflect this point in that line, so if I reflect it in that line, it's going to be somewhere up here. Okay, we could just call that point Q. Now, if you remember something about your inverse functions, when you reflect something in the line y equals x, what happens is the x and the y coordinates swap. Okay, so at this point up here, Q, if this was the point xy, this now becomes the point yx. Okay, and we'll see why that sort of happens. So if I drew in a right angle triangle here, remember that the height of my triangle is just whatever the y coordinate is at that point, and the base of that triangle is whatever the x coordinate is. Okay, now if I drew in a similar triangle up here, you should recognize that I basically have the same triangle that I've rotated. Okay, so I've got this nice right angle triangle here, okay? But now this length here is my length y, okay? And this is the height of the triangle is x. So this is another way to look at why x and y swap. Okay, now why have we done all of this? So that angle here, that's the angle pi on 2. So this bit here would be theta. So this whole thing here is pi on 2 minus theta. Okay, so I'm going to write a few relationships here. For this new point Q, okay, the angle that we get that is subtended by that radius at Q is pi on 2 minus theta. Okay, so if I look at rewriting that point as cos of pi on 2 minus theta, okay, remember that's equal to the x coordinate at that point, which is now y, right? Because we did our reflection. So that's equal to y, but y is equal to the sine of theta. So we get this nice relationship that the cos of pi on 2 minus theta is equal to the sine of theta, okay? And similarly, if I look at the sine of pi on 2 minus theta, that's now equal to my y coordinate, which is x, okay? So that's equal to the cos of theta, okay? So the sine of pi on 2 minus theta is the cos of theta. They're equal. They're the same value. And the cos of pi on 2 minus theta is equal to the sine of theta. Where I think this is like the easiest to understand is, if you remember from our exact values, okay, the cos of pi on 4, which is 45 degrees, is equal to the sine of pi on 4. And I can rewrite the cos of pi on 4 as the cos of pi on 2 minus pi on 4. That's equal to the sine of pi on 4. Okay, if you remember, they were both equal to 1 over root 2. All right, I'm going to summarize this for you, and we'll see how we use it with some other numbers and examples in a second. Okay, so now what we're going to do is we're going to have a look at another sort of similar relationship, okay? But this time we're going to reflect point P again. We'll reflect it in the line y equals x like we did before, but now we're going to do another reflection in the y-axis. Okay, so our point is going to end up sort of over here, if that looks like a reflection. Okay, so that point there, remember this became the point yx. So now if I reflect that, that's going to become the point negative yx, okay? Now negative y is the same as negative sine theta, and x is the same as cos of theta. Now that point there, like what angle is that, okay? So if that's reflected, this little bit here is theta, so this whole angle here is going to be pi on 2 plus theta. So now we can get some relationships between the sine and cos of pi on 2 plus theta. So let's look at cos of pi on 2 plus theta. Remember, that's always equal to my x-coordinate. And now my x-coordinate is the negative of sine theta. Okay? And then we've got, if we look at the sine of pi on 2 plus theta, that's always equal to my y-coordinate, which is now the cos of theta. Okay, so I get these two other relationships. So in summary here, you've got our sort of relationships with angles that are either plus or minus pi on 2 radians. Okay, so how might we use this? If we know that the sine of alpha is 0.9 and the cos of alpha is 0.4, what's the value of sine of pi on 2 minus alpha? So let's look at our relationship. The sine of pi on 2 minus alpha is equal to the cos of alpha. I've just used a different Greek letter for you there, okay? But sine of 2 minus alpha, that's going to be equal to the cos of whatever alpha is. So that's actually going to be equal to the cos of alpha, which is now 0.4. So the last relationship that we're going to look at here is called the Pythagorean identity. Now, remember Pythagoras' theorem is x squared plus y squared equals h squared, right? Where h is the hypotenuse, okay? Now, if we think in terms of sine and cos and our unit circle, we know that x is the cos of theta, y is the sine of theta, and our hypotenuse is the radius, right? Which is equal to 1. So if I substitute those values into Pythagoras' theorem, I get that cos squared theta plus the sine squared theta is equal to 1. Now, just a little bit of a notation. We don't really write cos theta squared, okay? I don't know why, but the notation is like this. Cos squared theta, but they mean the exact same thing. And we'll look at that, what means when we substitute some values in the next example. Okay, so this question says, given that sine of theta is a half, and this is telling us theta is between pi on 2 and pi radians. Okay, so that's telling us which quadrant our angle is in. So let's sort of investigate that first. Pi on 2 is here, and pi is here. So we're looking for an angle that is in the second quadrant, okay? And I'm just going to write in my ASTC because that's going to help me out in a second. Okay, all I know is that sine theta is equal to a half, and I want to find cos theta. So I need a relationship that relates sine and cos, which is my Pythagorean identity, okay? So we've got cos squared theta plus sine squared theta equals 1. Okay, cos squared theta, we don't know what that is. That's what we're trying to work out. But we know that sine of theta is equal to a half. So I'm going to do a half, and I've got to square it because it's the sine of theta squared. And that's equal to 1. Okay, and now I'm just going to go through and solve. So I'm going to, I'll work out half squared. So cos squared theta plus a quarter equals 1. I'm going to subtract a quarter from both sides. Okay, so that gives me cos squared theta equals 3/4. And now to find cos theta, I'm just going to take the square root of both sides. Just like if I had x squared equals 3/4, if I've got cos squared theta, to find just cos theta, I've got to take the square root of both sides. Now, when I take the square root of a number, I've got to consider that it could be the positive or the negative value. Okay, and this is where my quadrants are going to come in handy. I've been told that my angle is between pi and pi on 2. Okay, so only sine is positive in that quadrant. That means because I'm solving for cos, it has to be the negative of this value here. Okay, so negative square root of 3 on 4, or we should write that as root 3 on 2. Okay, and I've not been asked to find out what theta is. I just want to know the value of cos theta, so I've answered my question there. All right, guys, so that's this lesson here. We just had a look at the relationship between sine and cosine and the complementary angles and also the Pythagorean identity. So next, we are going to have a look at the graphs of sine and cosine, and we're going to look at our knowledge of the unit circle in order to sort of generate those graphs. Okay, those of you that live in Melbourne will probably recognize the iconic Melbourne Star. Unfortunately, at the time of this recording, the Melbourne Star is closed indefinitely, but who knows? We may see it reopen again sometime. But how does this relate to the maths that we're doing today? Well, the Melbourne Star, as you know, is a big Ferris wheel. It has a 110-meter diameter, and it completes a rotation or a turn every 30 minutes. So after one cycle, it repeats its journey again, another 30 minutes, and again, and again, and again, okay? So anything that has this kind of what we call periodic motion can be modeled by one of our trig functions, so our sine function or our cosine function. And we call these, you'll often hear the phrase circular functions because the motion of these functions has that periodic nature. There are a lot of things that come up in the real world that have this periodic nature. So things like tides coming in and out, the motion of waves, for example, looking at average daily temperatures or average number of sunlight hours, all of those things can be modeled by our circular functions. So they're very, very, very useful. So this lesson is going to be focusing on the graphs of sine and cosine. In this lesson, we're going to take a deep look at the sine curve and the properties of that function, and then we're going to look at the cosine curve. This is a bit of an introductory lesson, and I know you probably all will have seen these functions back in Unit 1, 2, and maybe even in Year 10. So it could be something that you go through quickly and just check your knowledge with the multiple choice questions, or if you want to really refresh your understanding of these functions, you can go through the lesson with me at pace. Okay, so we're going back to basics here, guys, with the graph of y equals sine x. We're going to graph this using our knowledge of the unit circle and a table of values to get some key points on this graph. Now, if you remember, when we talked about the unit circle, we looked at a point, any point P there on the unit circle. So if I start with just that first point that's on the x-axis, I can see that that's the point 1, 0. Okay, but we also learned that that point could be expressed in the form cos x sine x. So remembering that our y-coordinate is the value of sine x, okay? So that angle there is 0, okay? The x-axis angle is 0. So if I look at the sine of 0 degrees, the value of the y-coordinate there is 0, okay? Now let's look at some, I'm going to sort of skip through this table a little bit. I'm going to jump right to pi on 2 radians, okay, which is this angle up here. That's my 90 degrees, okay? Now that is the point 0, 1. Okay, so that means that the sine of pi on 2 radians is equal to my y-coordinate there, which is 1. So I'm going to start plotting these points here on my axes. So my first coordinates here are at 0, 1. Okay, and then the next set of points here I have is the point pi on 2 radians and 1. And I'll label this as 1 here and negative 1 here. So here's a second point on my y equals sine x function. Okay, you'll notice that the x-axis is labeled in terms of radians because that's what we're typically using here. We're not going to be using degrees much more in methods. Okay, let's keep going. I'm going to look at where sine is pi radians now. So that's this point over here. And if I write that point there is the point negative 1, 0. So the sine of pi, we know, is 0. Okay. So I'll fill that in my table and I'll plot that point. And we'll now go to the next set of angle here. This one all the way down here is 3 pi on 2 radians. That there is the point 0, negative 1. So the sine of 3 pi on 2 radians is a negative 1. And if I plot that point, it's down here. Okay, and now if I make one full rotation, I'm back to 2 pi radians, which is now this point here again, and so that is 0. So you can see I get these dots here, but I don't have a perfectly good idea of the shape of this curve. So what I'm going to do is I'm going to go ahead and I'm going to fill in a couple of the other angles just to get an idea of the shape. Okay, so I need to use my knowledge of exact values here, okay? And if you need to go back to that lesson, you can review your exact values. So I'm going to go through them quite quickly. So if x is pi on 6, I should know that the sine of pi on 6 is a half. Okay, so that would be about this point, say here, okay? Pi on 6 and a half, all right? The sine of pi on 3 is root 3 on 2. Which, if I plotted, would be about here, okay? Now, if I keep going, okay, I'm going to fill in the table with all of my exact values, and we can see how we plot these points. Okay, so I've filled in the table for you there, and I've done this sort of from 0 to pi radians. You get this shape like this. And now because of the symmetry of the sine curve, this is going to be just sort of a reflection of that part there. Okay, and if you wanted to go ahead and plot all of those yourself, you'll see that you get that shape. Now, remember we talked about the fact that this goes on forever and ever and ever. So it would just continue in the same way. Okay, that nice like wavy shape. And if we looked at our negative values, we would get something like this. Okay, and that's the graph of y equals sine x. So here's a much nicer looking graph of y equals sine x, and we'll just go through the properties of the sine function that you need to know. So first of all, the graph y equals sine x, it repeats every 2 pi units. So we call this the period of the graph, or the period of the function. So the period of y equals sine x is 2 pi. So it repeats every 2 pi radians. Okay. Now the maximum of the y equals sine x is at 1. And the minimum is at -1, okay? This means that the range of the graph is between -1 and 1, and we might write that like this. This also tells us about the amplitude of the graph. Now, the amplitude is the distance from what we call the center line. So the center line here would be the x-axis, okay? So the distance between the center line and the maximum or the minimum, they would be the same. That's our amplitude. Okay, so the amplitude of sine x is 1. We can also think of that as half of the distance between the minimum and the maximum. So we'll move on to the graph of y equals cos x, and we're going to construct it in a very similar way. So if we start with our first point here, remember this was the point 1, 0. Now we know the value of cos of x is the x coordinate, okay? So the value of cos of 0 is 1. Okay, so this time, and I'll label in here 1 and -1, the first point on my graph that I'm going to plot here is the point 0, 1, okay? Because the cos of 0 is 1. Now let's look at the cos of 90. So that's this point up here. That was 0, 1. The cos of 90 would be 0. Sorry, I shouldn't say 90. Pi on 2 and 0. Okay, my next point we'll look at is pi radians. So that's -1, 0. So the cos of pi radians is -1. And 3 pi on 2 radians, that's this angle or that point down there. So here we have 0, -1. So the cos of 3 pi on 2 radians would be 0. And if we go back to 2 pi, that's going to be exactly the same as 0, so 1. So the cos of 2 pi is 1. Now, you're kind of seeing something very, very familiar here. And I'll go ahead and fill in the rest of the values between 0 and 2 pi for you, or you can try them yourself, just based on your exact values. You can sort of test yourself and see if you know them off by heart. Otherwise, you can look at my filled-in table. So here's our table filled in. And if you plot some of those points, you're going to start to see a very familiar shape. Okay, so that's in between 0 and 2 pi. We get this sort of shape, and now I'll go ahead and plot some of the negative points. Okay, and there's my very rough sketch of the cosine curve. And you'll notice that it has the exact same shape as the sine curve. It's actually just been translated to the right by pi on 2 radians. So now we'll have a look at the properties of the graph of y equals cos x, and they're very similar to sine x. So just like sine x, the graph of cosine repeats every 2 pi units, okay? So the period of cos x is 2 pi, the maximum is 1, and the minimum is -1. So our range is between -1 and 1. And then the amplitude is also 1, okay? And as we said, the graph of cos x is just the graph of y equals sine x translated pi on 2 radians to the right. So that is your basic overview of the graphs of y equals sine x and y equals cos x. As I've listed the properties there for you, along with the domain and range. And I'd encourage you to sort of annotate this sheet with any of your own understandings about these two functions before we go on to the next lesson, which is looking at transformations of these curves. Okay, so I'm going to direct you to a YouTube video, which is on the YouTube channel Numberphile. It's one of my favorite math YouTube channels. And it's a really, really amazing, I think, explanation or presentation of the unit circle and how it relates to the sine and cosine curves. So it's about 12 minutes long. You don't need to watch the whole thing unless you really get hooked. But if you could watch the first about 5 minutes or so, I think this will really help your understanding of where the sine and cosine curves come from. So I hope you enjoyed that video as much as I do, and I hope it really solidified your understanding that, you know, the y coordinate of a point on the unit circle is the value of y equals sine x, and that the x coordinate of any point on the unit circle is cos of x. And if you kept watching, you maybe had a look at some other very interesting trig functions, tangent, which we'll look at later on in this series, and the reciprocal trig functions, which you don't look at unless you're doing specialist, but, could be interesting to look at. So in today's lesson, we're going to take the sine and cosine functions and we're going to look at a few transformations. So the transformations of sine and cosine work exactly like the transformations that you've learned for all of your other functions in your maths learning up until this point. In particular, in this lesson, we're going to just look at dilations and reflections. Okay, I'd love for you to start off just by sort of investigating functions where we have y equals a sine x, okay, where a is sort of any number. And I'd like you to try graphing on your CAS calculator or even on Desmos maybe, the graphs y equals sine x, y equals 2 sine x, and y equals 3 sine x. And I'd like you to try and make a conjecture, what does the value of a do to the graph? Now, I've asked you to graph these functions for this domain, okay? X is between negative 2 pi and 2 pi. If you're not sure how to change your domain or limit the domain, I'll show you that now on the CAS, but if you're okay with that, you can pause the video and go ahead and try graphing these functions now. All right, so the first thing that we'll need to check when we're working with our circular functions is that our CAS is in radians. So you can see mine is actually in degrees right now, but if I just click on where it says DEG, if I just click it once, it will turn to radians for me. Okay, now if you're looking for the trig functions on your calculator, they are underneath the control button. Okay, and we're going to look at sine first. And a reminder that no matter what variable is given to you in the question, when you're graphing things on the CAS, you must use the variable x. Okay, so if it was sine of theta or sine of t is often used, you need to make sure you're putting in sine x on your calculator. Now, if I just press enter now, okay, the calculator is just going to give it to me between negative 10 and 10, which is sort of the standard domain that the CAS calculator gives. But what we can do, a really easy way to change that is to just double click. So do you see where it says negative 10 here? I'm sort of hovering. If I double click that, it highlights it. I'm going to delete the negative 10, and I wanted to go from negative 2 pi, so 2, and here's my pi button, okay? And then this one's sometimes a bit tricky, but there we go, I've highlighted it. And I'll take away the 10, and I'm going to put in 2 pi. Okay. You can also go into your Windows settings to change this, and then you can just click anywhere on the graph there, and that will change. And usually because my sine x is going between 0 and 1, you could change the range if you wanted as well, but I'm just going to leave it for now for your exploration. There's other ways that you can change the domain as well. You can put it straight into the function when you're graphing using your such that. So you might have learned that way in your class. So using this up and down bar here, and that's when you're putting the function right into the graph. So I'll show you that this time. So if I go tab, the next function I asked you to graph was 2 sine x. Okay, so 2 sine x. I'm going to go outside. Okay, such that, and now I'm going to put in my domain. Okay, so you'll see that I've put the domain in there as an inequality, and I can press enter, and I get this function here. So I'll let you go ahead and graph the third one on your own, and then I want you to have a think about what you know already about transformations, and maybe write down for yourself, what do you think the value of a has done to change the function? Okay, so if you graphed all three of those functions, you should have got something like this on your CAS calculator, this screenshot here. And hopefully what you've discovered is that A tells us about the amplitude of the function, okay? So we know that in general, the amplitude of sine x is 1. But if I have 2 sine x, which is the black graph here, I can now see that the amplitude is 2. And for 3 sine x, the amplitude was 3. Okay. If we relate that back to our transformations, we would say that that's a dilation of scale factor A from the x-axis. So it's stretching the graph away from the x-axis. And the A value is also going to tell us about the range of the graph, okay? So the range of the sine function is going to go from negative A to positive A. Okay, and the same thing is going to happen to cosine of x. Okay, these two functions behave in very, very similar ways. If I had y equals 2 cos of x, that's going to change the amplitude of my function to 2. Now, one thing you do need to remember is that amplitude is always a positive value, okay? So if you had a negative value there, say it was negative 2 sine x, we would still say that the amplitude is 2, okay? It's a measure and it's always a positive value. Okay, so this time we're going to investigate again. We're going to look at cosine this time, and we're going to look at what happens when you have a coefficient in front of the x, okay? So cos of 2x, cos of 3x, cos of a quarter x. And I've given you 3 functions there. Similarly, I want you to practice graphing those functions on your CAS calculator, and then I want you to try and write down what you think the value of n does to the function. Okay, so hopefully you got something like this on your CAS calculator. Now, it's a bit tricky to look at, but if we look, the blue graph on my page is the regular y equals cos x, okay? Now, if we look at the red graph, we have cos of 2x. What we can see is the graph is sort of like squished in here, and what it's done is it's changed the period of the graph. Okay, and it's changed the period of the graph by a factor of 1/2. Okay, so the way that we find out the period of any of our graphs is we say it's normally 2 pi and we divide it by whatever the value of n is. Okay, so again, in this case here, the period of cos of 2x, so the period of this one would be 2 pi divided by 2, which is pi. So that means my graph now repeats every pi radians, okay? If we relate that back to our transformation language, we would say that this is a dilation of a scale factor of 1/n from the y-axis, okay? So it's compressing or stretching the graph either towards the y-axis or away from the y-axis. Now, the reason I got you to do this one here, the cos of x over 2, in this case, n is 1/2, okay? So to work out the period of this one, I would do 2 pi divided by 1/2. Now, remember, when I divide by a fraction, I have to multiply by the reciprocal. So this becomes 2 pi times 2/1, which is 4 pi. Okay, so you can see for this black graph here, that's actually been sort of stretched out. Its period is now 4 pi, so it only repeats every 4 pi radians. Okay, so remember that the value of n here, it is going to impact the period of your graph. For this example, we're going to state the amplitude, the period, and the range of the following functions. So let's look at A. Y is equal to 3 sine of x over 2. I would recommend that before you start answering the question, you get into the habit of first just identifying the value of A and the value of n. So in this case, A is 3 and n is 1/2. Okay, now A is a positive value, so I can say right away that my amplitude is 3. And from that, I can get the range of the graph. So the range now I know is going to be between -3 and +3. And then the period, remember, to get the period, I need to do 2 pi divided by n. Okay, and we've already seen this one. That is equal to 4 pi. Okay, so you might want to try B on your own first. So pause the video, give it a go, and then you can compare with my answers. So again, I'm just going to start this off by identifying A, which is a half, and N, which is 3. Okay, so the amplitude then is a half. And then from that, I can also tell that my range is between negative a half and a half. Okay, and my period is going to be 2 pi divided by n, or 2 pi divided by 3, which is just 2 pi divided by 3. Okay, so now we're going to move on by actually sketching the graph of one of these functions. So again, I'd encourage you to do this in a logical way. We'll start first by identifying our a and our n. So a in this case is a quarter. That's giving me an amplitude of a quarter and a range of negative a quarter to, square brackets, because we're including a quarter, to a quarter. Okay, and then the value of n is 2. So my period is 2 pi divided by 2, which is pi. So that means that this graph is going to repeat every pi radians. Now, another thing I need to think about is the domain that I've been given. So I need to go between negative pi to 2 pi. The next thing that you have to do, and this will get more complex as the functions get more complex, is think about how you're going to label your x and y axis. Now, I know that I need to go between negative pi and 2 pi, but I also know that my function has to repeat every pi radians. And then there's sort of 4 main points, or 4 divisions that I want to make for each cycle of my graph to get that nice wave shape. So the way that I might do this is go, okay, I know it has to repeat every pi radians, and I should be able to divide that pi into 4. And I'm not going to label every single line here, but there's my pi on 2, and then it's very clear that that's pi on 4 and 3 pi on 4. That's one cycle there. Now I need to go all the way to 2 pi, so I'll label this point, and I'll just label my halfway point as well. And then on the negative side, I just need to go to negative pi, and so that would be negative pi on 2. Okay. Now, the range, the y-axis, I should label in terms of looking at my amplitude, because that's going to tell me my minimum and my maximum values. So I'll just say, that this is a quarter and this is negative a quarter. So those are the sort of key points that you want to label before you start sketching your graph. All right, let's just look at the first sort of positive cycle of this curve. Now, it's the sine function, so I know I'm going to be starting at 0, 0. So that would be my first point there. Now my first quarter is where I get my maximum value. And then here is where I go back to 0. My next quarter is my minimum. And then I'm back at 0. So that's what I meant about sort of dividing the curve up into quarters, because you want to get those key points. So here's my first cycle of this curve. Okay, and once you've got that shape, you can then repeat it for however long you need to within the domain that you've been given. So my second cycle, I quite like to do some dots and things, but if you're just sketching, you don't need to worry about being too exact. So we're going to go up and back down. That point might be down there. And back up again. And then what we'll do is we'll do the same on the other side. So this time I'm going down first on my negative side. I go all the way down to here, back up to 0, back up to my maximum, okay, and to my end point. Try not to make it look pointy. Make sure you have a nice smooth curve. I'm maybe a little bit pointy there, but they definitely don't want to see this kind of points on an exam. You definitely won't get marks for having a sort of a smooth curve. Okay, so just like a parabola or any other curve, you need to make sure that you're drawing in curves and not sort of pointy things. Okay, so that's no good, bad. All right. So the next thing that we're going to look at is what happens when the value of a is a negative. And just like, again, like all of your other functions that you've looked at so far, if a is negative, that is a reflection in the x-axis. So it's sort of like flipped. So I've just drawn, or not, I haven't drawn these. These are from the CAS calculator. Here's two functions here. Sine x is your red curve, okay? And then you can see that negative sine x is just a reflection in the x-axis. But remember, even for this one here, the amplitude is still 1, okay? So even though I've got that negative in front of it there, I would still say the amplitude is 1, okay? And the range stays as -1 to 1 as well. Okay, similarly, we have here cos of x. So remember, cos of x starts up here, or that's the first sort of point on the y-axis at 0, 1. And then negative cos x is just a reflection, again, in the x-axis. Again, I'll emphasize it again, just so we don't make any silly mistakes. The amplitude is always going to be a positive value. So the amplitude of this blue graph here, the amplitude is still 1. Okay, so let's take a look at graphing a function y equals -4 sine of x on 2. So and in this case, my domain is going to be between -2 pi and 2 pi. Okay, so we'll start the same way we've started the other ones. We're just going to look at the value of a and the value of n and what that tells us about the graph. Okay, so a in this case is -4. That tells me I've got an amplitude of 4, and my range is between -4 and 4. And then I just need to keep in mind that that negative is telling me that the graph's going to be reflected. Now my value of n in this case is, you can see I have x over 2, so n is 1/2. That tells me about my period, which is 2 pi divided by 1/2, which is 4 pi. Okay, now what I like to do, and you can do this or not. So I'm going to change to a different color pen, but I quite like drawing the graph without the reflection first. So just as 4 sine of x on 2, and then drawing it a second graph with the reflection in. Okay, so my red is going to be the non-reflected graph. All right, let's take a look at my axes here. I need to go from -2 pi to 2 pi. So we'll go maybe pi here to 2 pi. And then I'll reflect that on the other side, -pi to -2 pi. And my range is going between -4 and 4. So I'll just make this 4 and -4. Okay, I know it looks like -3, but it doesn't really matter in this case, okay? Because that's all we need is the maximum and the minimum heights there. Okay. So I'm going to draw this without the reflection first, okay, because it's just a little bit easier. Now sine starts at, remember, 0, 0. Now in this case here, my period is 4 pi, okay, but I'm only going between 0 and 2 pi. So actually all I'm going to get here is kind of the first half of this curve because it's very stretched, okay, because of that, the period being 4 pi. So I'll just draw it like with dots, but what you would get here is this half of the function. And if we kept going, we would get like the bottom half of it going to 4 pi, but we don't need to draw that. Now we can just follow sort of what we've done with our curve here. My minimum value is going to come down here. That would be about this point here. And then back up to 2 pi. Sorry, that's a little bit messy, but that's not my real graph, so it's okay. And if you're doing this on an exam, you might just do like a very, very light pencil sketch of, your first graph and then add in some translations afterwards. So I'm going to switch back to my blue pen now, and I'm going to draw y equals -4 sine of x on 2, okay, which is just this graph reflected in the x-axis. So my minimum point now here is going to be here. So that's going to be 0 and 0. I'm just putting in some key points so I can sort of connect them nicely. Okay, so that's that half of the graph. And then I'll look at some key points here. At -pi, I'm going to have my maximum value, and then I'm going to come back to 0. And there's the second half of my graph. Okay, so again, that value of a there is just a reflection in the x-axis. Okay, so we also need to be able to write down the equation of our function from words. So you might get a list of transformations and you need to be able to come up with the equation. So what is the equation of the image of the graph of y equals sine x under a reflection in the x-axis, okay, followed by a dilation of scale factor a third from the y-axis? So I like to do this in steps. Again, you might like doing it a different way, but I like to start with just the first transformation that I'm given. So I'm going to do that in blue. Just a reflection in the x-axis would make this y equals negative sine of x. Now I'm going to take that negative sine x and I'm going to add in my next transformation, which is a dilation of a scale factor of a third from the y-axis. Okay, from the y-axis, that means it's in the brackets here. And it's a bit tricky here, but this is going to be the reciprocal of a third. So this becomes the negative sine of 3x with both of those transformations in there. And again, guys, this is no different to the transformations that you've been doing with all of your other functions, okay? So you just need to keep following the same rules that you would follow for any other function and just apply them to the trig functions. Okay, so guys, I've summarized for you here the properties of y equals a sine nx and y equals a cos nx. What I'd suggest that you do here is that you sketch yourself the sine or the cosine function and sort of label in your amplitude, your range, and that sort of thing, sort of tying all of these key properties together. Okay, next lesson, we're going to jump to solving trig equations, and then we're going to come back to some more complex transformations where we're looking at your vertical and horizontal translations. Okay, is it a trig question or is it a trick question? I think many methods students would say, is there any difference? I know this is a topic that comes up and can be sort of difficult, but I want to assure you, if you just follow logical steps, you'll be able to answer any trig, not trick question that VCA can throw at you. So today's lesson is on solving trigonometric equations, so equations involving any of the trig functions. We're going to specifically start by looking at functions that involve sine or cosine only. So we will do our solving trig equations in 2 steps. We're just going to start with some simple equations first, and then we'll build up to some more advanced equations in the second half of this lesson. Okay, so because sine and cosine are periodic functions or circular functions, and they can go on infinitely or forever, there's actually multiple solutions to trigonometric equations, okay? What I've got here in front of me is a graphical solution of the blue curve there. The blue curve is the function y equals sine x. And that green line there is just the equation y equals 0.5. So altogether, what we have is we have the solutions to where is sine x equal to 0.5. And you can see just in this sort of like limited domain I have here, so I've just got from negative 3 pi up to 3 pi, you can see that I have 1, 2, 3, 4, 5, 6 solutions. And if I kept going, I would have more and more solutions, okay? So often what we're going to do is we're going to restrict the domain in our trig equations. So you're going to know in what specific domain are we solving for x. So if the domain given, say, was, if this was, find the solutions to sine x equals 0.5, where x is between 0 and 2 pi, we would know that we're just looking for the solutions in this part of the graph, okay, between 0 and 2 pi, and you'd be able to see that you should have 2 solutions here. Now, there is a way to solve for when we have no specific domain, but that's going to come up in a much later chapter when we look at the general solution of trig equations. Okay, so for this lesson, we are going to have a specified domain. Okay, so to start off, we're going to be solving our trig equations following sort of 3 steps, okay? So the first thing that we always need to do is we need to rearrange our equation so that it's in the form sine x equals something, some number, or cos x equals some number. And that's exactly the way that we rearrange an equation to solve for x, okay? So in this case, we're just first solving for sine x or for cos x, okay? Then what we do is we find what we call the reference angle, okay? Or sometimes it's called the base angle. And we're going to do this either using a calculator, or for now we're going to be doing it using our knowledge of exact values, okay, without a calculator. Because it's obviously much harder to do it without a calculator. The reference angle is basically just your first acute angle. So a reference angle is a positive acute angle, so an angle between 0 and pi on 2 radians. Okay, and then what we do is we use that reference angle and we use our 4 quadrants to find all of the solutions within our given domain. Okay. Now, I'm going to suggest to you that when you're doing some practice questions that you then use your CAS calculator to check your answer, because that's just a very good way for you to practice using the CAS to solve trig equations, just so you get some practice in here. But it's definitely something that's almost probably going to come up in paper 1, and we do need to be able to do it by hand, okay? Okay, so let's read the question together. It's a very good idea to make sure that you take note of the domain that's given in the question, okay? That's very important. So we have solve 2 sine x is equal to root 3, and we want for x between 0 and 2 pi. Okay. So let's take a look at my steps. The first thing I need to do is I need to rearrange this equation so that I've just got sine x on its own is equal to some number. So I can do that first by dividing both sides of the equation by 2. Okay, so if I divide this by 2 and this by 2, what I get is sine x is equal to root 3 on 2. Okay, so that's step 1, done. Now what I need to do is I need to use my knowledge of exact values to work out, like, for what angle x is sine of x equal to root 3 on 2. So basically what I'm doing is I'm taking the inverse sine of root 3 on 2. Now, if we had our calculators, super easy, we can just put that in our calculator, but we should recognize that root 3 on 2. And if we don't, you might go back to some sort of way that you've used to memorize your exact angles. I always love going back to my triangles. So if we go here, I know I've got a right angle triangle here. I always think to myself, it was half of an equilateral triangle with a side length of 2. That is 1, and that is root 3 there. Now I'm looking for which angle is sine going to be 3 on 2. So I need the angle that's going to give me the opposite is 3 and the hypotenuse is 2. So that's this angle here. That I know is the angle 60 degrees or pi on 3 radians. So that's my base angle. And the examiners are going to be looking for you identifying your base or your reference angle somewhere within your working. Okay, so my base angle there is pi on 3. Now, because I'm looking at a positive value, root 3 on 2, my first solution is actually going to be pi on 3. And now I'm going to use my quadrants. So I'll label these here. I'm looking for where sine has a positive value, right? Because root 3 on 2 is a positive value. So where is it positive? It's positive in this quadrant. So that was my initial pi on 3 radians. And sine is also positive in this quadrant here. So I'm going to draw that equivalent angle here, which is pi minus pi on 3, which is 2 pi on 3 radians. Okay, so that's going to be my second solution, 2 pi on 3 radians. Now looking within my domain, 0 and 2 pi, so that's one whole sort of rotation here. There are no other quadrants where sine gives me a positive value, so I know those are my only 2 solutions. So we're going to check our previous solution to this using our calculator now. So we go to the home page and we go into our settings and we go to our document settings. And if you scroll down here, do you see the calculation mode here is on approximate? We want to change that to exact, and then that's going to give us the answer in the format that we want, okay? And that's going to give it to us as a fraction and in terms of pi. here's my function. I've restricted the domain. Pressing enter, you can see I get x is equal to pi on 3 or x is equal to 2 pi on 3, which is exactly what we got when we did it by hand. Okay, so if you have your calculator, you can also solve any equation graphically. So I'm going to go through with you how you would do this. So I've listed the steps there. You're going to draw the graph of y equals 2 sine x. So that's the left-hand side of the equation. And then you're going to draw the graph of y equals root 3. We should change the scale of the x-axis to fit our domain. And we could change the y-axis if we wanted to as well. And then we're going to find the points of intersection between our two graphs, and that will give us a graphical solution of this equation. Okay, so we're first going to put in our first, the left-hand side of that equation, which was 2 sine x. Okay, and then we're going to put in the second equation. So we use the tab button to get a second graph. So that was a square root of 3. Okay, and now I'm going to change my domain. So this, I wanted it to go just from 0. So I'll change that to 0. And I want it to go up to 2 pi. So 2 pi. Okay, and now I can see here that I've just got two solutions there. So to find those exact points, we would go menu, analyze graph, and then intersection. Okay, and now it's going to ask you to set your lower and upper bound. So my first intersection point is between there and there, and you can see that I get 1.05. Now, unfortunately, the CAS won't give you that intersection point as a fraction, but we did see when we solved it before that the first solution was 1.05. That is equivalent to pi on 3. You have a calculator, so you can check that the decimals and the exact values are equivalent. Okay, so that's my first solution. And then I'll do the same thing around where that second intersection point is. Okay, and I'll just grab that point and pull it down so you can see it clearly. And that was 2.09, which is equivalent to that 2 pi on 3, which was what I got for my second solution. So there we have, I think, visualizing or looking at the graph, it's really important for you to see why there are two solutions within that given domain there. You can clearly see where those two, sort of the left-hand side of the equation and the right-hand side of the equation, that curve and those graphs intersect at 2 points, and those are the points that we got by hand. So look, I can't stress enough how important it is for you to practice using your CAS calculator as much as possible. So whenever you're doing a question by hand, it would be great if you checked your answer using your CAS, and even better if you did it graphically, just to practice using the graphing functions. Okay, we'll go through one more worked example. I'm going to do it by hand, and then I'm going to encourage you to check your solution using your calculator. Okay, first step, remember we need to rearrange our equation so that it's in the form cos x equals something. So to get cos x by itself on the left-hand side, we need to subtract 1 from both sides of our equation, which gives us cos x equals -1/2. Okay, now this one's a little bit trickier. I've given you a different domain, and I've given you cos x is equal to a negative value. We still need to think about our base or our reference angle, okay? And our reference angle is where our cos or our sine is equal to the positive value here, okay? So where is cos x equal to 1/2? All right, if we know our exact values well, we know that cos x is equal to 1/2 when x is equal to pi on 3. Okay, pi on 3 isn't a solution because we're not looking for where cos of x is equal to 1/2. We're looking at where it's equal to -1/2. Okay, we're just using that pi on 3 as our base angle, but I would encourage you to write that part down because that's usually what the examiners are looking for your first mark when you're solving these equations. Okay, so let me write in my acronym here, and I'm looking for where cos now is negative. Okay, so cos is negative in this quadrant and in this quadrant, and I'm also looking within this domain, so from -pi to pi. Okay, -pi, remember, is going this way. Okay, so if I'm looking that would be from 0 to negative pi, okay, in that sort of range there. So I'm only going to have a solution for cos in my third quadrant down here, okay? Now I draw in my sort of reference angle, which is pi on 3, okay? And what I'm doing to calculate this whole angle here, that's got to be negative pi plus pi on 3. Okay, a little bit tricky when we're thinking about the negatives, so you need to maybe stop and do it like quite carefully. We actually want the angle as measured from the x-axis. Okay, so that there, negative pi plus pi on 3 would be negative 2 pi on 3. So that's my very first solution. Okay, now let's look at, I need to go all the way to positive pi. So between 0 and positive pi, that's going this way. And I've only got a negative solution for cosine in the second quadrant, okay? So I'm going to draw this angle in here. And again, my base angle, my reference angle is pi on 3. So this whole angle here is pi, okay, minus pi on 3, which is 2 pi on 3. Okay, so that's my second solution. Okay, and there's no other solutions within that domain. Okay, now what I would like you to do is get your CAS out, and I want you to try and solve it using the solve function, and then I want you to try and solve it graphically, okay, and see what happens. Okay, so if you were having any trouble, you can have a look here, but to put this in your calculator, remember we just use our menu algebra solve, and then we put in our domain, and we get here x is negative 2 pi on 3 or x is 2 pi on 3, just like when we solved it by hand. And then if you look at the graphical thing, you can sort of see why we get those two solutions in the places that they are, okay? So negative 2 pi on 3 was this negative 2.09, that sort of first solution in the negative side, and then we get 2.09 on the positive side, okay? So really good to make those connections between the equation and then the graphical representation of it. Okay, so now we're going to get into some more advanced trig equations. Again, there's quite a few steps that I've written out here. I'll go through them quickly now, but they'll make a little bit more sense once we actually start solving the equations. So we're looking at now equations where we have sort of, instead of just cos of x or sine of x, we've got something in there for that angle. Okay, so there's a few more steps that we have to follow when we have this sort of scenario. Okay, so the first thing that we want to do is we still want to rearrange the equation. So we have sine of whatever that angle is, or cos of that angle, equal to some value c, some constant value. And then what we're going to do is we're kind of just going to forget about what's in this bracket, and we're just going to replace it with a big letter x. And then we're going to go through and solve for that big x like we normally do, using our reference angle, our exact values, and we're using our quadrants, our ASTC, to find the other solutions. And then we're going to go back and re-substitute back in this a, whatever was in the brackets there, for x, and then we're going to solve for our actual angle x, okay? We do always want to check, this one's a little bit trickier with the domain. We just want to make sure that we go back. Our sixth step is that we check that our final answer is within that given domain. Okay, let's give it a go. Okay, so here we have solve sine of 2 theta, okay, is equal to root 2 on 2 between 0 and 2 theta. Now, before we go into solving something like this, we're just going to take a look at like what this means. So remember, now that we have 2 theta here, okay, that, remember, affects our period, okay? So if we think back to the graph of sine of 2x or 2 theta, the period of this graph is actually 2 pi divided by 2, so it's pi, okay? So if I were to do a bit of a sketch of sine of 2 theta, so my x-axis is theta, my y-axis is y. Let's have a look. So I'm just graphing here y equals sine of 2 theta, and I'm just going to go between 0 and 2 pi. Okay, so let's label this as pi and 2 pi, and my amplitude hasn't changed, so I'm just going between 1 and -1 again. Okay, now I know that I'm going to start with sine at 0, 0, and I'm just going to draw a few little dots in here to give me an idea of what my graph looks like.
So this is the first cycle of the graph, okay? And then I'm going to have another identical cycle. Now, if I look at the right-hand side of the equation, I'm going to just draw in y equals, so this is going to be a straight line, root 2 over 2. So root 2 over 2, that's going to be some value like less than 1. Let's just say it's about here. And you can see that within this domain, I'm actually now going to have 1, 2, 3, 4 solutions, okay? So that value there, that period, that changes the amount of solutions that we would have within a given domain, okay? So again, if the equation's like quite simple, it's nice for you if you can graph it. If you don't have your calculator, you can kind of give yourself a bit of a sketch so you know how many solutions you're looking for. You don't have to do this step, but it's helpful. I think it's helpful. Okay. All right, so now let's have a look at how we would solve something like this without a calculator. Okay, so I've already got my equation in the right form. I've got sine of 2 theta is equal to root 2 on 2. My next step here is I'm going to ignore that 2 theta, okay? And I'm just going to say, let x equal 2 theta. And I'm going to now just solve sine of x is equal to root 2 on 2. And I'm going to go through and solve this the way I normally would, okay? So I'm looking for where is sine of x equal to root 2 on 2. My base angle there is pi on 4. Okay, and because it's a positive value, I can use that pi on 4. Now, because I let x equal 2 theta, I need to reconsider my domain here. Okay, so now my domain is actually going to be 2 theta is equal to, because I've doubled that angle, I've got to double the endpoints of my domain. Okay, so 0 doubled is still 0, but now I'm going to be looking between 0 and 4 pi when I find my initial solutions. Okay, so let's see what this looks like. So my base angle there is pi on 4. I'm going to use my 4 quadrants to find my other solutions within this domain. So I'm looking for where sine is positive. So first I'll identify the quadrants that I'm working in. Okay, so that's quadrant 1 and 2. So pi on 4 would be here. And then my next angle would be pi minus pi on 4, which would be this whole angle here, 3 pi on 4. Okay, so that's going to be my second solution, 3 pi on 4. Okay, now because I have doubled my domain, I actually have to go through now to 4 pi. Okay, so what happens here? So this is 2 pi. I can keep going here to get another angle now, because remember 4 pi is going to be like 2 rotations of the unit circle. Okay, so this first sort of purple angle that I've drawn in here, this is actually 2 pi plus my base angle, plus pi on 4. Okay, so that would be 8 pi on 4 plus pi on 4, which is 9 pi on 4. Okay, and you can see we start to get into a lot of fraction work here. So this is why your teachers are probably always going on about being good at fractions. It really comes in handy in this section. Okay, so we've got 9 pi on 4. And within that domain, okay, there's actually going to be a 4th angle, which we know because we already sketched the graph. Okay, so I'll just draw this one in red. So going around and around and around, I get that angle there. And that red angle that I've drawn there, that's actually, so if I was going in my second cycle, that's 3 pi. Okay, so 3 pi, I'll just do my working out down here, minus my reference angle, which was pi on 4. Okay, so 3 pi would be 12 pi on 4 minus pi on 4, which is 11 pi on 4. And that's my 4th angle. Okay, so there are my 4 solutions. But we've actually solved for big X. What we need to solve for is theta. Okay, so here's what we do. We now need to go through and replace 2 theta where we had in that big X. Okay, so what I'm saying is 2 theta is equal to those 4 solutions, but I want to solve just for theta. So what I've got to do is I've got to divide by 2 for every single solution, okay? So pi on 4 divided by 2 would be pi on 8. 3 pi on 4 would be 3 pi on 8, and 9 pi on 8. and 11 pi on 8. So now if I go back to my original domain, which was between 0 and 2 pi, I can see that all 4 of these solutions are now within the domain that I wanted between 0 and 2 pi. So we made the domain bigger to fit, our replacement of x equals 2 pi. But if we've done everything correctly, our answers should fit within our original domain, okay? And if we go back to the drawing that we had, or the sketch that we did, okay, I can see that these are going to be my pi on 8, 3 pi on 8, 9 pi on 8, right? So that's just over pi and 11 pi on 8, okay? Okay, so if you'd like, you can try this one on your own. You could pause the video and then check your solution with me or with your calculator. Otherwise, you can follow along for a second example if you need another walkthrough. Okay, so we've got solve sine of 2x plus pi on 3 is equal to a half. And this was a question that was on a VCA exam, okay? So we'll go through the question and then I'll tell you how the students fared on this question. Okay, so because we've got sine of lots of stuff, 2x plus pi on 3 is equal to a half, we're just going to replace that with x first as our first step. Okay, and then what we should also do is we need to now consider how our domain changes with this replacement. So we're now saying 2x plus pi on 3, so x, or a big X, is going to be within this domain. So it's going to be 2 times 0 plus pi on 3, so pi on 3, and then we're going to do 2 times pi plus pi on 3, so 2 pi plus pi on 3. So that's the same as saying 6 pi on 3 plus pi on 3, which is 7 pi on 3. Okay, if you're like me and you like to do a little bit of working off to the side, that's perfectly okay and encouraged. Okay, so 7 pi on 3 is our new domain. Okay, once we've done this replacement, it's quite a nice, easy little equation here. We just have sine of big X is equal to a half. So let's think about, first of all, where is sine of x equal to a half? Okay, so knowing your exact values, you should know that your first solution there would be pi on 6. So let's draw that angle in here, pi on 6. Now, the problem here is that pi on 6, that's actually outside of our domain. So that's not going to be one of our solutions, okay? So, I forgot to write my letters in here, my very helpful letters that tell me where the value of sine is positive. Okay, so that's in this quadrant and this quadrant. Okay, so the next quadrant that I'm going to look to is this one here. And that's going to give me the angle pi minus pi on 6, okay, which is 5 pi on 6. Okay, so that's going to be my first solution. Okay, now we need to go all the way to 7 pi on 3, which is just over 2 pi. So let's see what happens if I go just over 2 pi here. My next angle would be 2 pi plus pi on 6, okay? And that is less than 7 pi on 3, okay, because it's less than 2 pi plus pi on 3. So that would be my second solution. So that would be, if I add those together, I get 13 pi on 6. Now, if I keep going, I'm going to be outside of my domain there. Okay, so those are my only two solutions. Okay, 5 pi on 6 and 13 pi on 6. Now, all I've solved here for is big X, but I need to actually solve for this little x that's in my equation. So I'm now going to replace that 2x plus pi on 3 for big X. So what I've got to do now to solve for little x is I've just got to do exactly what I would do if I was solving any equation. So I've got to isolate x, okay? The first thing I'm going to do now is I'm going to subtract pi on 3 from both of my solutions, okay? So that's going to leave me with 2x equals 5 pi on 6 minus pi on 3. We can think of pi on 3 as 2 pi on 6, okay? So 5 pi on 6 minus 2 pi on 6 would be 3 pi on 6. My next solution would be 13 pi on 6 minus 2 pi on 6. So that would be 11 pi on 6. And now to get x on its own, I'm going to divide both of those answers by 2. Okay, so x is equal to 3 pi on 12 and 11 pi on 12. And I should just write that first solution. Instead of 3 pi on 12, I should reduce my fraction. So finally, I get pi on 4 and 11 pi on 12 as my final solution. Okay, so this is probably as complicated as it gets in terms of solving trig equations. So everything's going to be some sort of version of this. Now, on the VCA report, they said that most students were able to identify the correct reference angle. Okay, so they somewhere on their in their working had identified that you've got to work with pi on 6, but most students were not able, and only 31% of students were able to get down to the correct final solution. And this is because of errors with adding and subtracting fractions a lot of the time, or not considering your given domain. So if we look back at the domain we were given, 0 and pi, we can see that pi on 4 and 11 pi on 12, they fit our domain. So some students might not have given enough answers, or some might have given too many answers, some solutions that are outside of the domain. So really tough question here, but if you follow it quite methodically and work slowly through each step, then you should be able to get to the correct final solution. Hopefully you're in that 31% of students that get there. Okay, this is the kind of question that VCA like to put on the calculator paper. And instead of just asking you to find the solutions to the equations, they put a little twist in there. So find the sum of the solutions to 2 cos of 3x is equal to root 3 within that given domain. So I'm going to show you how you can do this on your calculator fairly quickly. So to solve this, or to do this quite quickly, what we're going to do is we're going to use the zeros function instead of the solve function when we get our solutions here. So the zeros function is just the function that we use if we have an equation that is set equal to 0. So we need to think about rearranging our equation so that it's equal to 0, which would just be subtracting that root 3 from both sides. So if we go into the menu, and then we go to algebra, we can see this zeros function. Okay, so now I'm going to write in my equation. So it was 2 cos of 3x. Now remember to use the multiplication sign here, 3 times x. And now I'm going to say minus root 3. Okay, and I'm solving that for x, so I'm still going to put in my comma x. And now I'm going to add in my domain. So if you remember, we do control equal sign to get my such that line. Okay, and then I'm going to put in the domain as an inequality, so between negative 2 pi and pi. Okay, so now when I hit enter, I get the list of my solutions sort of as a set. And this is going to help me to sum those answers very quickly so that I can answer this question. Because what I wanted, remember, was the sum of the solutions, not just the solutions. So I can just type in the word sum if I want to find the sum of something really quickly. Okay, and then I'm going to open brackets, and I'm going to use my arrow keys to go up to highlight what I want the sum of. Now when I press enter, I get all of those values in as a sum, and then I can press enter again, and my final solution is negative 83 pi over 18. Okay, you could do this a bit more manually, but that's just a quick way to find the sum of a large number of solutions, okay? But you do need to remember that you've got to use the zeros function instead of the solve function. If you try using the solve function, your calculator gives you each individual answer as x equals, x equals, x equals, instead of it being just as a set here. So you won't be able to then use the sum function if you try using the solve function. So you've just got to remember that little trick. Okay, guys, so I've just listed a few key skills there. There's that solving trig equations, it brings together a lot of things, okay? First of all, just solving equations in general, you're following the same sort of steps, but you also then need to know your exact values, you need to know how to use the unit circle and your ASTC to find multiple solutions. You need to be able to work with fractions, and it's good to have a basic understanding of your trig function, so the graphs of sine and cosine. And then I've relisted listed the steps to follow there, but of course those steps are in my words. What would be good for you is for you to now go through and maybe even make your own set of steps that you, in your words and in your language, you could put into your bound reference, or that you would just have so that you've got an understanding of how you go about solving these trig equations. All right. So we're now going to go back to looking at some graphs, and we're going to get into some advanced graph sketching. When a sound is made, say on a musical instrument, it produces vibrations in the air. So these vibrations vary depending on the sound, and particles that are vibrating because of the sound cause other nearby particles to vibrate, and so on. So these vibrating particles make up what we call sound waves, okay? And sound waves travel at different speeds and with different variations in pressure through the air. But a sound wave, how it's related to math, can be modeled by a sine curve. So what I've got here for you are the sine waves that represent the note A, the note C sharp, and the note E. But if you know anything about music, you know that you're probably not always playing these notes in isolations. You might play chords. So if we put all three of those notes together, we get that crazy looking function at the bottom there. And this is called a sum function. We've added all three of these sums, these sine waves together to create another wave. So we're going to be looking at sum functions at the end of this lesson. But here's that's just an interesting application of where we might see these in real life. So this lesson is called Advanced Graph Sketching. So we're putting almost everything together that you've learned about trigonometry and functions and transformations of functions together so far. And the reason that we did trig equations in the lesson before this is that we're going to be using this skill in order to find the x-intercepts of our transformed graphs. So strap yourselves in. This is a big one. Let's get going. So we've already looked at our reflections and our dilations. So the last type of transformation we need to add in here are our translations. So we'll look at our horizontal translations in the direction of the x-axis, and we'll look at our vertical translations in the direction of the y-axis. And then what we'll do is we'll add in finding our x and y intercepts for any graph and the endpoints of the graph given any domain. And then, like I said, we're going to look at sum functions, or you might know this as addition of ordinates. So this is just a recap of the transformations we've already done. So as we know, the value of a, so that's the value that's being multiplied in front of the function, that tells us about the amplitude of the graph. And that's also what we call our dilations from the x-axis. Okay, we remember if a was negative, that gave us a reflection in the x-axis. Okay, then we looked at what happens to n. So this is the coefficient of x inside the brackets, and this is a dilation from the y-axis. And remember, it changes the period of the graph. Okay, so if you do need to go back to the lesson on transformations of sine and cosine functions to review those things before we start, I would encourage you to. But if you're ready to move on, we will do that now. Okay, we're first going to look at our translations parallel to the x-axis. So this is if we're moving the graph left or right, okay? So when we have a graph of this form here, where we have a sine of nx minus b, this value here, b, tells us about our translation parallel to the x-axis, okay? Now, it's really important to keep it sort of straight here, that if I have something like this equation here, x minus pi on 4, that is a translation to the right by pi on 4 units. So you can see my original graph here has been, so my original graph is the blue one, y equals sine x. And then if I have sine x minus pi on 4, that's every x coordinate there is moving to the right by pi on 4 units. Okay, we can also call this the phase shift of the function. Okay, so the first question just says, what's the sequence of transformation that takes the graph of y equals sine x to the graph of y equals 2 sine of x plus 4? Okay, now the first thing is you always want to make sure that x is on its own here. So if I had something like sine of 2x plus pi on 4, I would first have to factor out that 2, and you've done this with other functions. Okay, this would be x plus pi on, if I divide out 2, I get pi on 8. Okay, so just make sure that it's in that form first, but we don't have to worry here. We just have x on its own, so we're good. Okay. The other thing is when you're describing the sequence of transformations, you should be doing this in a certain order. We talk about Dr. T at my school, so we first go dilation, reflection, translation. So I'm going to look and see if there's any dilations here, and I can see that there's one. And that's what that 2 is giving me there. So what I've got is I've got a dilation of factor 2 from the x-axis. Okay, there are no other dilations here because I don't have a coefficient of x, okay? The only other thing that's happening here is this plus pi on 4. So that's my translation, and that's going to be parallel to the x-axis in the negative direction, okay? So you can probably write this in a variety of ways, but we'll try and sort of stay consistent with our language here. So okay, so we just want to get across somehow that it's like a horizontal translation. It's pi on 4 units, and we're going to the, oh, that's my left. Okay, I think your left is if I point this way, but we're going in the negative direction of the x-axis. Okay, so really important to just be very clear when you're talking about your translations. Okay, so this time we want to find the equation of the image of y equals sine x if it's undergone a dilation of a factor of a half from the y-axis, okay, from the y-axis, followed by a translation pi on 6 in the negative direction of the x-axis. Okay, let's take a look at how we might build this. So I think I showed you in another video that I like to do this step by step, okay? So I would have been starting with sine x. Let's just put that first transformation in. So a dilation of a factor of a half from the y-axis. This is the one that goes sort of within the function, okay? So y equals sine of, it's going to impact what's in here with the x. Because it's a factor of a half, we need to take the reciprocal of that number, okay? So instead of a half, I would have 2x, okay? Now I'm going to build in my translation of pi on 6, okay? And here's where we need to maybe be a little bit careful. We would have sine of 2. To show that translation of pi on 6, I need to open the brackets again and just do it within this x. I want my phase shift of pi on 6 within the function like that. Okay, so those are pretty tricky, I think, to kind of get your head around. There's actually something that I did wrong, which is a common mistake, and maybe some of you have spotted it. Because I'm going in the negative direction of the x-axis, that should actually be plus pi on 6. So well done if you caught that mistake. You can see it's very, very easy to do. Okay, so there's my full sort of equation of the image once it's undergone those two transformations. Okay, now we're ready to add our last transformation in, and this is our translations parallel to the y-axis. So this is when we're shifting up or down, okay? And so when we have a constant term, so a plus or minus something added to the end of the function like that, that value of c tells us whether or not we're going up by a certain number of units or down, okay? So, and in this case here, it's exactly as you see it. So here, I have y equals sine x, okay? If I want to draw the graph sine of x plus 1, I'm just shifting that graph up by 1 unit. Now, when you're sketching these functions, one thing that is helpful to keep in mind is we know that the graph of y equals sine x, it's got this like, it's called different things, the sort of a principal axis or a center line, but basically the x-axis or the line y equals 0, you know, it cuts exactly right through sine of x, okay? So sine of x kind of goes around that line there, y equals 0, okay? So what happens when I shift a graph up, okay, when I have a vertical translation, is that center line also moves up, okay? And I'll draw it in red for the translated graph, but you can see that if I just drew in the line y equals 1, and you don't need to draw these on your graph, it can just help when you're doing vertical translations. You can see now that that line's just been translated up, and I've got y equals sine x plus 1 now sort of, equidistant from that center line to the maximum or to the minimum point there. Okay, my amplitude doesn't change, okay, unless I've got something that changes, unless I've got a dilation in there. It's just that the graph is exactly the same, shifted up or down, okay, by whatever c is. Okay, so let's try and draw a graph here. We've got y equals 2 cos of 3x minus 1, and then we're going to sketch it. Okay, so the amplitude of the graph is 2. All right, that's easy. A is 2, amplitude is 2. Now, we've got this minus 1 here, okay? So that minus 1 is going to affect the range of the graph. Normally, if I didn't have that minus 1 in there, my graph would go from -2 to 2, okay? And maybe what I'll do is I'll use a few different colors here. Like if I had y equals 2 cos of 3x on its own, we know the range would be from -2 to 2. But now because that graph is being shifted down by 1, the range is also going to move down by 1, okay? So my new range for this graph is going to be -2, take away 1, so -3, and then 2, take away 1, which is 1. Okay, so now instead I'm going from -3 to 1, okay? What's the period of the graph? Well, the period is going to be 2 pi divided by 3. And we have no phase shift to worry about here. Okay, it's actually very mean, I think, if they give you a graph with both a vertical and a horizontal shift. It's pretty rare for them to put all the transformations into one exam question. I'm sure it could happen, but we're just going to deal with them one at a time for now, okay? All right, so how would we draw this graph? Now, like I said to you, I like to draw these in stages. So the first thing I'm going to do is in blue, I'm going to draw the graph y equals 2 cos of 3x. And then I'm just going to shift that graph down by 1 to give the graph that we want. Okay. All right, so I'm going from 0 to 2 pi, but I know that my period is 2 pi and 3. So that means I'm actually going to go, okay, here's 2 pi. And I want to divide that into thirds. That's going to be 2 pi on 3 and 4 pi on 3. Okay? Because if I have a period of 2 pi and 3, what that means is I'm going to have 3 cycles of that cos graph within 2 pi. Normally I just have 1 cycle, but that 3 is telling me I've got 3 cycles. Okay, so within this, remember, in order to draw it neatly, we want to divide each cycle into 4. Okay, and my first stage is I'm just going to label sort of my -2 to 2. So remember, I'm doing it without the vertical translation first. Okay, so if I do my cosine, I'll just do a dotted line here. There's my first cycle, and then I'll go through and draw 2 more. Not super even, but we get the idea. My next step is I'm going to add in my vertical translation, and I'm going down by 1. So I'll put in my new range. So it's going to go shift down by 1. And if you can imagine now, my center line or my mean point, my mean line is now going to be at y equals -1. And again, I'll just draw a little dotted line in here. If you're doing this for yourself, you might just draw it really lightly with your pencil, just so you can get an idea of what you're drawing around. So all of these main points, they're going to move down by 1. So this one's going to go from 2 to 1. That's going to go from 0 to -1. That's going to go from -2 to -3, and so on. So we can draw in all of our main points like we did before, and that can help us to draw the graph a little bit more accurately. Okay, and then finally, I'll just join up those dots. Okay, and there you have it. We've got the graph of y equals 2 cos of 3x minus 1. Okay, so remember that I said it would be a little bit mean to have everything, all of our transformations in one graph. Well, of course, it would be remiss of me not to do an example like that with you guys. If you think you're ready for it, by all means, please stop the video and see if you can sketch this graph on your own. At the moment, we're not worrying about our labeling our exact intercepts or our endpoints. That's going to come next. We just want the general shape of of the curve with these transformations sort of obvious to us. Okay, if you want to just stick with me, let's have a go. We're first going to think about what is our amplitude, what is our range, what is our period, and what is our phase shift. So that's not what we're going to do first. What we are going to do first is we're going to make sure that this equation is written in the right format. So I can see here that I've got this 2x, which means that I need to factor that 2 out first before I start thinking about any of these transformations. So I'm going to rewrite this as y equals root 2 sine of 2x minus pi on 4 plus 1. Okay, now let's think about what we've got going on here. A is root 2, so the amplitude is root 2. Okay, I've got this vertical shift up 1, so that means my range is also going to be shifted up 1. Okay, so normally my range would have been minus root 2 to root 2. Okay, but because of that vertical shift, I've got to add 1 to each of those values. Okay, and we don't have a calculator. We're going to just leave that as an exact value. So my range is going from minus root 2 plus 1 up to root 2 plus 1. Okay, the period of my graph is 2 pi divided by 2, so pi. Okay, and I've got a phase shift of pi on 4 to the right. Okay, I'm going to show you how to do this in stages because that's how I like doing it. If you think you can do it all at once, go for it. I'm going to do it first without any translations. Then I'm going to add in my horizontal translation. And then finally, I'm going to add in the vertical translation. Okay. Now, I need to go between 0 and 2 pi. But my period is pi. Okay. I'm going to divide up each of those sort of cycles into 4. Okay, and now I'm going to go with what my range would be without any vertical translations. Okay, so I'm going to go from negative root 2 up to root 2. Okay, so the first version I'm going to draw is just y equals root 2 sine of 2x. Okay, no translations. So that would just look something like this. Okay, there's my first cycle between 0 and pi, and now I'm going to draw the second one. Okay, step 1 is complete. If I was to go down on that side there, that's negative pi on 4, okay, and that would be our sort of minimum value there, all right? And if I kept going, I'd have another pi on 4 to get to my maximum, okay? That's important because I'm going to be shifting this graph now. Okay, so the next thing I'm going to add in is that horizontal translation, okay? Okay, so I need to move everything pi on 4 to the right. So that point moves there, that point moves there, that other point that was outside of my domain is now here, and so on. So I'll just draw in my points. Okay, so you can see my green sort of dashed line is just shifted over to the right by pi on 4 units. And now my last step is going to be adding in that vertical shift up by 1. So I'm going to draw this in a red pen because I've already written that equation up at the top in red. Okay, so what do I need to mark in here? I need to add 1 to my minimum and my maximum values. So I'm actually going to make this go up a little bit higher, but we'll say this is root 2 plus 1, and we'll just go up, say, to here. Here's negative root 2 plus 1, and then I'm going to shift the x-axis up by 1 as well, okay, just to give me an idea of where this curve is sitting. So now I'm taking that green curve, okay, and I'm moving all the y-coordinates up by 1, okay? So, for example, this point, which was at 0, negative root 2 is now at 0, negative root 2 plus 1. Okay. That point has moved up here. We've moved up here. Okay, and the reason I've done this is it just sort of keeps it straight for me. Using different colors means I'm less likely to make any sort of error. So let's now connect these with a red solid line. Okay, and there we have our fully sort of shifted and translated graph. Okay, the last stage in sort of sketching a graph is, as with any of your other graphs of functions, we need to make sure that we're labeling our axis intercepts, or our x and y intercepts, and then also our endpoints. Okay, so to find our axis intercepts, you do this exactly the same way that you find any other axis intercepts for any other function. So to find the y-intercept, we let x equal 0 and solve for y. To find the x-intercept, we let y equal 0 and solve for x. Okay? To find our endpoints, we look at our domain. Okay? So for any domain, AB, what you would do is you would set x equal to a and solve for y to find an endpoint, the first or the leftmost endpoint. And then you would let x equal b to solve for the second endpoint. Okay, if you didn't quite follow that, it's going to make a lot more sense once we start using numbers. So let's get into our first example. Okay, the last thing you might need to label on a graph like this are the endpoints. Okay, so for the endpoints, you're looking at your domain. Okay, so the first endpoint is going to be when x is equal to 0. And we actually calculated that on the last slide, didn't we? When x is equal to 0, I had this point here, which is negative root 2 plus 1 and 0. Now, my second endpoint is when x is equal to 2 pi, right? That's the end of my domain. Now, you're probably looking at it saying, it looks the same. And it is the same because of the symmetry of the graph. You could, however, I wouldn't ever just like sort of eyeball these things. What you would want to do is sub that point in. We go 2, and now I'm subbing in that endpoint, 2 pi minus pi on 2 plus 1. This becomes 4 pi minus pi on 2. Plus 1. Now, because of the unit circle and all of that symmetry, sine of 4 pi minus pi on 2, if I drew that in, so I've got 4 pi would be along the x-axis, minus pi on 2 is that angle there, okay? Okay, so that the value of sine there is negative 1, and that's why we get the same answer that we had for this endpoint here, okay? All right, so this endpoint here we would label as 2 pi negative root 2 plus 1. Okay, and we're done. We have a fully labeled graph. Okay, the last section of this lesson is just looking at addition of ordinates or sum functions. You've probably seen this before with other functions, and it's exactly the same sort of idea or technique. So we can use addition of ordinates to graph the sum of two functions that we are familiar with, okay? So we can do f of x plus or minus g of x to get a new function, h of x. The way that we're going to do this is we're going to sketch the graphs of f of x and g of x, and then what we do is just add the y coordinates of the two functions at some particular or obvious x values. All right, let's take a look at that. Okay, so here we have, we want to sketch the graph of y equals 3 sine x plus 2 cos of x. And what I've done here, first of all, is just drawn for you. 3 sine of x is our blue curve, okay? And 2 cos of x is the green curve there. All right, now I've already done sort of the x and y coordinates for each of these two graphs, so we can sort of see how this is done. Now, we're just going to look at some very obvious or points or sort of key points. And the points I would encourage you to look at are, first of all, where you have any x-intercepts. So for example, do you see at this point here, where x equals 0, we have this y-coordinate is 0, and this y-coordinate is 2. Okay, so all we need to do is just add those y-coordinates together. Okay, 0 plus 2 is 2. All right, so that's going to be a point on my sum function. All right, now the next one I've looked at is where these two graphs intersect. And basically, if they intersect at that point, they have the same y-coordinate. So the y-coordinate will just double at that point. So that's another one that would be good to draw in here. So what we could do is we could just kind of visualize this. This is just below 2. If I doubled it, it would be just a bit below 4. It might be somewhere there. Okay. Now that is not actually this point here, pi on 4. Pi on 4 might be a little bit over to the right. But at pi and 4, y equals 3 sine x is 3 over root 2. And y equals 2 cos x would be 2 over root 2. So at that point here, you get the point 5 on root 2. Okay, so you might have 5 divided by root 2. So 5 divided by about 1, it's probably going to be somewhere very close actually to this point, just above there. Okay, so either of those ways where you have a known point or where you have an intersection point, those are good ones to graph. Okay, you can see here at pi on 2, I've got 0 and this one is at 3. Drawn that in the table here for you. So again, you would get a point on your graph being here. You might look at some other points, like this one here is at 0 and -2. So that'll be another sort of obvious point there. Here you might look at, you're just going to have to eyeball some points, but like, to get this point here, you can see that this blue line, like the x or the y coordinate is bigger than the y coordinate here. So it's like you're taking that like y coordinate away. And so you might have a point there. Here, again, you have another intersection point. So you might like double. So you're kind of like doubling the y value here. Here, this would be 0 plus this point. So you're going to get another point here. And then you would get another point up here, okay? This is kind of, and I've done it in a table of values here. This is kind of, obviously, if you're just adding 0 to all of these, you just get the same point, okay? So it is not an exact science, okay? I'm going to tell you that right now. And I would encourage you to maybe even look at some of these functions once you've drawn them, because you sort of might get something like this, okay? But generally, you're going to be looking at where the two graphs intersect, okay, or where one of the graphs goes through the x-axis, and that's where you can find some really obvious points. All right, so we've covered a lot in this section. The most important thing is you getting your head around all of your translations, again, or transformations. They work exactly the same as your transformations that you've been doing with all of your other functions up until now in methods. You just need to apply them to your trig curves. So hopefully this summary page is useful for you. There's a couple of tips at the bottom there, a couple of reminders, but really just practice, 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 and then check any of your sketching of graphs with your CAS calculator, and that will really help you to understand this topic. So next, what we're going to do is we're going to look at where we're given a graph, and we just need to come up with the equation or the rule for that graph. So as we've discussed, we can use these circular functions to model behaviors that are periodic in nature, okay? So average daily temperatures would be one such behavior that follows a circular function, a sinusoidal sort of function. It could be sine or it could be cos, okay? When we model a function, okay, so this is like what happens in real life. We don't start with an equation. What we do is we collect data, we map those data points, and then we try and find a function that best fits our data points, okay? So what we're going to do today is sort of like what we would do to find the model for a function. We're going to start with a graph, and then we're going to go backwards, or is it backwards? I don't know, but backwards to find the equation of the graph. So today's lesson is called Finding a Rule from a Graph. We want to find the equation of a sine or a cosine curve. So we're going to do this in 2 steps. First, we're going to just look at determining the amplitude and the period from an actual graph, and then we're going to go right into writing the actual equation or the rule for that graph. So if we know the amplitude and the period of a graph, it can help us to find the rule for that graph. Okay, so just a reminder for us, the amplitude is half of the distance between the minimum and the maximum points of a curve. And we can use an equation for this to determine the amplitude. And that's just the maximum value minus the minimum value divided by 2. Okay, we can also have a look at the period of the function. And remember, we've learned this equation before, that the period is 2 pi divided by n. So often what we're going to be doing now is we need the n for the rule. Okay, so we need to make sure we understand that we could rearrange this to be n is equal to 2 pi divided by the period. Okay, but we'll come back to that. Okay, so here we have a function, and we're told that it has the rule y equals a times the cos of nx. Now, any of these functions can actually be written in terms of sine or cosine. So you will be told in the question whether or not you're going to be working with sine or cosine. Okay. All right. Part A says, what is the period and the amplitude of this function? So to work out the amplitude, we're going to do the maximum. So the maximum value here is 3. And we're going to subtract from that the minimum. So here's my maximum. Here's my minimum value. And then we're going to divide that by 2. Okay, so 3 minus 3 is 3 plus 3, which is 6, divided by 2 is 3. Now, you probably could have just looked at that graph and said, oh, the amplitude is 3 just by looking at it. But just in case it's not that clear for you, that's how you would use the formula. Okay, so we can see that because it's a cosine graph and it's starting at the maximum value, it's not been reflected. Okay, so we know that A then in our rule is 3. All right. So the next part we're going to do is to find the period of the graph. Okay, so the period is the distance that it needs to go for one full cycle. So we can look at one full cycle by going from the distance between like one maximum to the other maximum, or we could do the same if we can see the minimums. So on this graph here, you can see that the distance from that maximum to that maximum is 8, right? Because we're going from an x coordinate of 0 to an x coordinate of 8. Okay, so my period here is 8. And I know we're used to seeing pi within the period, but we don't have to have it. And in fact, when we start working within application questions, we might not have pi in there. So in this case here, we just have a period of 8. Now, that doesn't tell you my value of n, okay? That tells you the period. So remember that the period, we'll write out the equation, is 2 pi divided by n. In this case, we know the period is 8. So if I want to work out n, I need to rearrange this equation. So I get n is equal to 2 pi divided by 8, which is pi on 4. Okay, so that's all the working out for part A. So now I'm just going to put in my values for n and for A into the rule. Okay, so the rule is y equals a, so a was 3, times cos of nx. N is pi on 4 times x. Okay, you might also see this written as 3 times cos of pi x over 4. They both mean the same thing. Either of those answers would be acceptable. Okay, so that's it. Okay, so in this next section here, we're just going to go a little bit further where we might have a more complicated graph, putting it all together to find the rule for a function. So as I said before, any circular function or any sort of function in terms of sine or cos can be expressed in terms of one or the other. So you can see I've just got an example here. This curve here, we could say it's 2 sine of x minus 1, or we could say it's 2 cos of x minus pi over 2 minus 1. Okay, so again, you will be given whether or not you're working in terms of sine or cos. Okay, so in order to find the rule for a circular function, you're going to use your knowledge of the period and the amplitude to calculate a and n. That's what we just did in the last section. You're going to think to yourself, is this graph reflected or not? That's going to tell you if a is positive or negative. And then you're going to use any other points given to determine a value of C or D, and that's your phase shift or your vertical shift up or down. All right, let's look at an example. So the question says the graph shown has a rule of the form y is equal to a sine of nx plus c. Find the values of a, n, and c, and hence find the rule for the graph. All right, let's look at what we could start off here. What do we know? First of all, we know that this is a sine curve. Okay, and we also, what else do we know here? What can we see? We can see sort of like a minimum point here at 1, -1. We can see a maximum value here. This is the 0.33, and these will be obvious for you. Okay, if they're not obvious, then they're probably not like an exact point. And then we've got another minimum value here at 5, -1. Okay, so this is going to help us to, first of all, let's determine the amplitude. So remember, the amplitude is our maximum minus our minimum divided by 2. Okay, so my maximum value here is 3 minus my minimum is -1 divided by 2. That's 4 divided by 2, which is 2. So my amplitude is 2. And you can sort of see this. Obviously this graph has been translated by C units. You can probably tell what C is just by that line I drew in there, but I've drawn it in just so I can show you. Like that's our center line, and you can see the difference from the center line to the maximum is 2. Okay, my amplitude is 2. Now I'm working with sine, and if I just draw the basic sine curve for you, sine starts at 1, 1, as long as it's not been shifted left or right, and it's not been shifted, okay, because we just have nx, it's not plus or minus anything. But it normally goes up to the maximum first, okay? And this curve here is starting, at our on our y-axis, it goes down to the minimum value. So that's a signal to us that this graph has been reflected in the x-axis, okay? So that means my value of a is -2. Okay, so very careful that you need to check that. The next thing I can have a look at is my period. Okay, so the period of my graph, I can see here from one minimum point to the next minimum point, there's a difference of 4, right? From there to there is 4. So that's my period. And remember, that will help me to work out the value of n. Okay, so n is equal to 2 pi divided by my period. So 2 pi divided by 4. So n is pi on 2. Okay? Now let's fill in what I know so far. So I've got y is equal to a, which is -2, sine of pi on 2x plus some value c. Okay, you probably know what c is, but I'm going to take you through it just in case it wasn't obvious, okay, how you would look at it algebraically. Now what you can do is you could pick any point on this graph and substitute it in for x and y to solve for c. So the most obvious point that you could choose here is one of your axis intercepts, okay? So very clearly there, we've got 0.01, okay, on that graph. So I'm going to sub in the 0.01. Okay, so y is 1, x is 0, plus c, and I'm going to solve for c. Now look at what happens here. Sine of pi on 2 times 0 is 0. Sine of 0 is 0. -2 times 0 is 0. So this whole thing is just 0. Okay, so I end up with c is equal to 1. Okay, and again, just looking at that graph, you could probably tell that it's been translated up 1, but it's always good to check algebraically. So now I've got y is equal to -2 sine of pi on 2x plus 1, and there's my rule. You do need to be able to do this by hand. What would be really great is if then you drew the graph or in your CAS calculator and made sure you got exactly, the picture that's given to you in the question here. So this time we don't have a picture, we just have lots of words, okay? And we've got to figure out the rule for this function. So let's read it together. A function with the rule y is equal to a cos of nx minus b. So I do have a phase shift this time, where a, n, and b are elements of the real number system that are positive, okay? So that r plus is just telling us that they have to be positive numbers, okay? So hint, hint, there's not going to be a reflection in this one because we don't have a negative value for a. And we're also told that b is between 0 and pi on 2, okay? Including 0 and pi on 2. So we need to make sure when we get a solution for b that it's within that interval there. Okay, and we're told that the function has the following properties. The range is between -2 and 2. The period is 2 pi on 3. And then we're given a point when x is equal to pi on 6, y is equal to 2. Now we need to find a, n, and b, and then the rule for the function. Okay, if the range is -2 to 2, you should automatically be able to see there that the amplitude is 2, okay? If you can't, the range is giving you your maximum and your minimum. You're just going to use your equation. Remember, the amplitude is the maximum minus the minimum. 2 minus -2 divided by 2, which ends up being 2, okay? Now, because we know a is positive, we know then that a has to be equal to 2. Now, the period is 2 pi on 3. So from that, we can calculate n. We'll do it in a different color. So we get n is equal to 2 pi divided by 2 pi on 3. So that's 2 pi times 3 over 2 pi. Okay, multiply, flip and multiply. The 2 pi's cancel out, so n is just 3 in this case. Okay, now we're going to write the equation with what we have so far. Okay, so we have y is equal to 2 cos of 3x minus b. All right. So now we're going to substitute in that third piece of information. When x is equal to pi on 6, y is equal to 2. So we get 2 equals 2 cos of 3. X is pi on 6, so we substitute in pi on 6 minus b. Okay, now let's kind of neaten this up a little bit. So the first thing I'm going to do is just multiply 3 times pi on 6. 2 times cos of, so 3 pi on 6 would just be pi on 2. And I can divide both sides by 2 to get 1 is equal to cos of pi on 2 minus b. Okay, I'm just going to rewrite this so it's, I don't know why I need to do this. Maybe not all of you need to do it. I like having the cos on the left-hand side is equal to 1. So let's just kind of replace here. Cos of x is equal to 1. We don't need to worry about a domain here because we're actually just looking for one solution for b where it's between 0 and pi. So we'll check that at the end. Okay, where is cos equal to 1? Okay, you can either think about your cosine curve. It's pretty easy in this case. Cos is equal to 1 between 0, and at 2 pi. Okay, so x would have to be equal to 0 or let's say 2 pi. Okay, I can already tell 2 pi is going to be too big for my range here, but we can leave it in just to check. All right, now I'm going to sub back in pi on 2 minus b is equal to either 0 or 2 pi. So to solve for b, I'm going to subtract pi on 2. And again, okay, we're just going to leave this because it's definitely outside of my range that I need for b. And then I can divide both sides by -1 to get b is equal to pi on 2. Okay, and you can see here that b can be between 0 and pi on 2, including 0 and pi on 2, so that sort of works there. Okay, so now we've got everything we need. We've got a, we've got n, we've got b. Now we can write in our final equation. So we have y equals 2 cos of 3x minus pi on 2, and we're done. All right, guys, so in summary, if you want to find the rule of a sine or a cosine graph, first off, look at your key properties. So look at your amplitude and your period. Then from that, you can work out your value of a and your value of n. Look for any reflections, okay, to see if a is positive or negative. And then you can use key points to determine any of your translations up and down or left and right, okay? I've got the formulas for you there for amplitude and period. And the next thing we're going to look at, you're probably thinking, what's happened to the tangent function? So we are going to focus a little bit more on the tangent function in the next lesson. Okay, you know we love a good math pun here at Edrolo. If you can work this one out, you can probably guess what today's lesson is about. So we're going to be taking an in-depth look into the tangent function in this lesson. So as I said, we're going to be looking at the tangent function. Specifically, we'll just look at the graph of y equals tan x. Then we'll look at solving some equations with tan, and then we're going to be looking at transformations of the tangent function. So to start with, we're going to go way back to our knowledge about the unit circle and some of our exact values so that we can see where the shape of the tangent function comes from. So if you remember, we've got our unit circle here, and I'm just going to place a point here. And remember, any point on our unit circle can be expressed in the terms cos x and sine x. So if we recall, tan is just equal to sine over cos, right? I'll write that in here for you. So the tan of any angle is equal to the sine of that angle divided by the cos of that angle. So we're going to use that relationship to work out some of the key values of tan x. So let's start right here where I've started, where we have the angle 0, okay? So this point here is the point 1, 0, okay? So if I'm doing sine over cos, so tan of 0 would be the sine of 0, which is 0, over the cos of 0, which is 1. So that's just equal to 0, okay? So the tan of 0 is 0. So I'm going to mark that point in on my graph. So we've got our point going through the origin there. Okay, I'm going to skip now up to the angle pi on 2, okay? So this point here is the point 0, 1. So what happens when we try to calculate now the tan of pi on 2? Well, that's equal to the sine of pi on 2 divided by the cos of pi on 2. So the sine of pi on 2 is 1 divided by 0. And you should automatically say to yourself, dividing by 0, we can't do that, right? So actually what we get is that this value is undefined. There's no value for the tan of pi on 2, okay? So I'm just going to write in U and D for undefined, okay? And what that gives us is, that gives us an asymptote on our graph, okay? So I'll draw in a little dotted line here, and I've got an asymptote at pi on 2. Let's keep going around the unit circle. So let's have a look at the angle pi degrees now, okay? So this is the point -1, 0. And if I do sine over cos, you should see that I get 0 divided by -1. So I'm at 0 again. So I'll mark in that point there. Okay. Let's now have a look sort of at our negative angles, okay? So I'm going to look at the angle negative pi on 2. So that's down here, negative pi on 2. So that's the point 0, -1. And you'll see I run into the same problem that I had with pi on 2 radians, okay? When I try to do sine over cos, I get -1 divided by 0, which again is undefined. So again, I'm going to have another asymptote at negative pi on 2, okay? And if I keep going to negative pi, that's this angle here, right? That would be negative pi degrees, okay? So that's also going to be 0. It's the same of tan of pi, so that's 0 as well. So I get this here. Okay, so I've got a couple of points, and I've got a couple of asymptotes, and if we keep going around and around the unit circle, we're going to follow the same sort of pattern. So I'm going to just add in, I would have another asymptote here. I'd have another point at 0 there. I would have another asymptote here. And there we go at 0. So just looking at this, you can kind of see that my asymptotes are spaced, like the difference between there and there is pi radians, okay? So the period of this graph is going to be pi radians. But what's happening in between these asymptotes, it's really hard to tell with just the points that I've given you so far. So let's take a look at some of the angles in between 0 and pi on 2 and pi and so on. So if I take this angle here, okay, that's our pi on 4, all right? At that point, we should remember from our exact values that sine and cos are the same, okay? They're both √2 on 2. So if I want to calculate the tan of pi on 4 radians, it would be √2 over 2 divided by √2 over 2, okay, which sounds really complicated, but it's just 1, right? Anything divided by itself is 1. So what I get here is at pi on 4, we'll just say that's, say, 1 there, and that's -1. So at pi on 4 radians, I've got a point here at 1, okay? Now what happens is as I move along this curve, okay, the value of cosine starts to approach 0, okay? That means my denominator gets smaller and smaller and smaller, okay? And when that happens, it means the actual value, when I'm dividing by a very small number, it gets bigger and bigger and bigger. So what happens to the tan function at that point is it starts to approach infinity, okay? And it approaches infinity all the way, you know, until we get to that asymptote. Okay, so you end up with a sort of shape of a curve like that, okay, on that side. The reverse sort of happens if we look at the negative angle. But if I look at this angle here, negative pi on 4, okay, that's going to give me a tan value of -1. And the same thing happens, except we start to approach negative infinity in this case. So we get this sort of curvy, sort of S-shaped line like this, okay? And then that repeats every pi radians. So we end up with a function that looks like that. This would start here. If I was just going up to 2 pi, we could end it there, okay? And then the same thing happens with our negative angles. Okay, and that's where the tangent function comes from. Now, you might recall from, I think it was lesson 6, when we were looking at sine and cosine, I referred you to a number file video. If you go back to that video now, they do a really good explanation of where the tangent function comes from as well. It's super interesting, probably more interesting than what I just showed you here. So I definitely would encourage you to have a look back at that one. Okay, so just to summarize here we've got the graph of y equals tan x, and we've got the properties of that graph. So the period, like I said, for tan is pi. So be very careful here, because for cosine and sine, remember the period was 2 pi, but for the tangent function, the period is just pi. It repeats every pi radians. Okay, we also have these asymptotes. Okay, so the first positive asymptote is at pi on 2 radians, and then it repeats every pi radian. So 3 pi on 2, the next one would be 5 pi on 2, and so on. And then we can do the same thing on the negative side. The first negative asymptote is at negative pi on 2, and then we go every we subtract pi radians to get the rest of the asymptotes. Okay, the range of y equals tan x is all real numbers. Okay, but we have a restricted domain at the asymptotes that we don't have with sine and cosine. Okay, so those asymptotes mean that tan doesn't have any value at those angles at pi on 2 and 3 pi on 2 and so on. We also have axis intercepts, so where it's intercepting the x-axis at x is equal to k times pi, where k is any sort of integer value. So what that means is, if, say here, k was equal to 0, the first axis intercept is at 0, okay? If k is equal to 1, the next axis intercept is at 1 times pi, which is pi. And you can see those are these axis intercepts that I'm talking about here. Okay, so yeah, that's it. That's basically your tangent function. So the next thing that we're going to have a look at is solving equations involving the tangent function. And guys, we're not learning anything new here, okay? This is exactly the same steps that we had when we were solving equations that had sine and cosine in it. The only thing that we have to sort of add in or remember here are some of our exact values for tangent, okay? Okay, so in this example, we're going to solve the equation tan of 2x minus pi on 4 minus root 3 is equal to 0. And we're looking for solutions for x in between 0 and 2 pi. Okay, the first thing we're going to do is we're going to rearrange this equation. Okay, so I've just added root 3 to both sides. And then what I'm going to do is I'm going to just ignore what is inside the brackets for now. Okay, so I'm going to let big X equal that big mess in there, okay? Just to make it a little bit easier for ourselves. So now I'm just going to solve the equation tan of big X is equal to root 3. But I've got to remember that I need to consider a new domain now, okay? So to each of the endpoints of my domain, I need to multiply the endpoint by 2 and subtract pi on 4, okay? So before we had... now we're sort of solving for our big X here. Instead of going between 0 and 2 pi, the lower bound is going to be 2 times 0 minus pi on 4. So just minus pi on 4. Okay, and the upper bound is going to be 2 pi times 2, so 8 pi minus pi on 4, which would be 15 pi on 4. Okay, so my solutions for big X are going to be now in between this domain. Okay, I need to know my exact value for where is tan equal to root 3. So the first thing we need to do is consider our reference angle. Where is tan of x equal to root 3? And we should know that is equal to pi on 3. Okay, and that's within my sort of original domain here. Now I need to work out the other solutions for tan within that domain. So I'm going to set up my quadrants. Okay, and I'm looking for positive values of tan because root 3 is positive. So tan is positive in this quadrant and in this quadrant. Now my lower bound was negative pi on 4 radians, so that would just be going a little bit into our fourth quadrant. There's not going to be any solutions for tan that are positive in that quadrant, okay, because tan isn't positive in there. So we're going to keep looking at our positive angles here. So our first angle was pi on 3. So my second solution is going to be, well, this whole angle here, okay, down in the third quadrant. And that one would be pi plus pi on 3, which is 4 pi on 3. Okay, I need to keep going because my my sort of upper bound here is 15 pi on 4, okay, which is almost 4 pi. So my next angle would be, I'm going all the way around back up to here, which is 2 pi plus pi on 3, okay, which would be 7 pi on 3. And I can fit one more angle in before I get to the end of my sort of my interval for x. Okay, so if I go all the way around to this angle now here, that's going to be 3 pi. So this would be 3 pi plus pi on 3, okay, which would be 10 pi on 3. Okay, and those are all the angles that will be within those two bounds. Okay, but that was big X. We actually need to now go and solve for our little x. Okay, so let's just replace in here. We had let big X replace 2x minus pi on 4 equals all of these angles. Okay, now what we want to do, the first thing that we're going to have to do is we're going to have to get rid of this minus pi on 4 by adding pi on 4 to each of our solutions. If you're like me, you have to do a little bit of working out if you've not got a calculator here over to the side. I'll show you how I would do the first one, and then I'll just fill in the remaining 4. So our first one was pi on 3. And I want to add pi on 4 to that. So my common denominator there is going to be 12. So this becomes 4 pi on 12 plus 3 pi on 12, which is 7 pi on 12. Okay, I'm sure your math teachers are always going on about you knowing how to work with fractions, and this is one of the main reasons why. Okay, so my first solution there is 7 pi on 12, and I'll just go ahead and fill in the other 3. Okay, we're nearly there. The last thing we have to do is we just have to divide each of these answers by 2 to get x by itself. So for the first one here, 7 pi on 12 divided by 2 is going to be 7 pi on 24. Okay, we just need to double our denominator to show the dividing by 2. And again, I'll go ahead and fill in the remaining 3 answers. Okay, and there we have it. We should now go back and look at our original domain, which was x has to be between 0 and 2 pi. And if we check, all of these solutions are between 0 and 2 pi. Now we should also remember, if I was drawing the graph of this function, this would be my x-intercepts. Okay, when you're solving for x, what you are finding on the graph are your x-intercepts. So don't forget to make the connection there between the equation and the graph of the function. So in this last section, we're going to have a look at transformations of the tangent function, okay? All of your transformations that you've been doing for all of your other functions in this course apply in the exact same way, okay? The only thing that we have to consider that maybe is a bit different with tangent is that we've got to consider our asymptotes, but we're going to looking at our period. Is there any translations? Is there a reflection? And then we're going to look at our x-intercepts and coordinates of the endpoints if we need to. Okay, so I'm just going to take you through sketching this graph. We've got y equals root 3 tan of x minus pi on 2 plus 1, and we've got a domain of x being between negative 3 pi on 2 and 2 pi. Okay, let's take a look first at the period of this graph. Now we know the period of tan is always pi, and we would divide by n. So n would be if we had any sort of like coefficient of x there, but we don't. So the period in this case is just pi. Next, we're going to take a look at any of our other transformations. Now, we've got this root 3 here, which is a dilation away from the x-axis. That means it basically stretches our tan function, but there's not a lot to show here on that graph. It's not like sine and cosine where you could show that the amplitude changed. Here we would just have a graph that's growing a lot faster, but it's not really going to affect our sketch very much, okay? But we'll write down the transformation anyway. So we've got a dilation of scale factor root 3 from the x-axis. The other thing we have here is we've got this minus pi on 2, okay? So that's a translation, pi on 2 radians, and it's going to be moving to the right, okay? So in the positive direction of the x-axis. Okay, and then the last transformation that we've got to consider is this +1 here. And that +1 is going to be a translation vertically, so it's going to be moving up 1 unit. Okay, so the next thing we should consider is our asymptotes. Now, because there's no change to the period, the asymptotes are still going to repeat every pi radians, okay? Now, usually our first asymptote is at pi on 2 radians, okay? So normally our first one is at pi on 2, but because we have that horizontal shift, we're going to actually add that shift, which was pi on 2 radians, to get our first asymptote at pi. Okay, so what I'll do is I'll start to label here. We can call this one pi and this one 2 pi. So here's my first asymptote at pi. Here's another one at 2 pi. We've got this one at 0 then, and then I would go negative pi. And then this last point here would be my negative 3 pi on 2. I'll just label that in because it's one of my endpoints. Okay, so we're starting to kind of get an idea here. Now let's have a look at where our x-intercepts are, because that's going to help us to start to get a feel for what the shape of this function looks like. So to find the x-intercepts, we want to set the equation of the graph equal to 0. Okay, so the first step I'm going to take is I'm going to rearrange this equation. So it's just tan of something is equal to something else. So I'm going to subtract 1 from both sides and then divide by root 3. Okay, so what I want to solve for is where is tan of x? We'll just ignore the inside bit for a second. Where is tan of x equal to negative 1 on root 3? Well, my base angle or my reference angle there is pi on 6, but this time I'm looking for where tan is negative. Okay, so tan is negative in the second and the fourth quadrants, so I'm looking for angles within this quadrant. So my first positive angle would be pi minus pi on 6, which is 5 pi on 6. And then my second positive angle would be 2 pi minus that pi on 6, which is 11 pi on 6. Okay, now I've got to look at some of my negative angles here because I really want the x-intercepts that are falling within my domain. So my first negative angle would be negative pi on 6. And then my next one would be, let's have a look here. That would be negative pi minus another pi on 6, so negative 7 pi on 6. Okay, now this was for the angle x minus pi on 2. If I want to find x, I've got to add pi on 2 to each of those angles. So 5 pi on 6 plus another pi on 2. So that's going to be 3 pi on 6. So that will give me 5, 6, 7, 8 pi on 6, which simplifies to 4 pi on 3. Okay, the next one there, 11 pi on 6 plus pi on 2 would be 14 pi on 6 or 7 pi on 3. And actually 7 pi on 3, if you'll look, that's actually more than 2 pi. So that's not going to be one that we're going to plot for this graph. Okay, my next two angles, if I add pi on 2 to each of those, gives me negative 2 pi on 3 and pi on 3. Okay, so let's have a look and we're at plotting those and we can sort of start to see where our graph is going to take shape. So 4 pi on 3, that's just over pi, or like sort of a third over pi. So that's going to be this point here, 4 pi on 3. Okay, so my graph is going to cross the x-axis at that point. Okay, negative 2 pi on 3, that might be right here. And then we've got another one at pi on 3, which would be, say, here. Okay, now remember that my graph was translated up by 1. So that means like where the graph would normally go through the x-axis is up 1. And you can just draw this in very, very lightly. It might help you to get a nice shape of your graph, because that's where the graph would have that little point of inflection. So what you get here is you get this sort of like, but we would have something like this sort of repeating and so on. And now all we really want here is we want to think about, this will probably follow the same sort of shape, but what is that endpoint there going to be? Well, we can't see what it's going to be. Actually, let's calculate it. So to find that endpoint, what we would do is we would take the equation of our graph, and we're going to substitute x is equal to negative 3 pi on 2 in for x. Okay, so this simplifies in here to being negative 2 pi. The tan of negative 2 pi is just 0. So we end up here with a y coordinate of 1. That should just say equals 1. So actually what I've drawn here is not correct. What we're going to have is this point here going up like that. So that point we should label negative 3 pi on 2, 1, because it's one of the endpoints of our graph. Okay, so that's probably like the most maybe complicated type of graph you're going to get on an exam or anything like that. We've almost got every type of transformation in there, but it gives you a good idea of the steps that you can take when you're trying to graph any of your trig functions, but in particular the tangent function. Okay, for this question, we were given that a function has a rule y is equal to a tan of nx. It has a period of pi on 4, and then we're told that when x is equal to 3 pi on 16, y is equal to 2. We want to find the values of a and n. Okay, since we know our period, we would start with n. And remember, we should know the relationship by now that the period is equal to pi on n. Okay, so we know the period's pi on 4 is equal to pi on n. That gives us that n is equal to 4. Okay, now that we know n is equal to 4, we can put it into our rule. And then that's going to help us to solve for a. So now we can sub in this information here for x and y. Okay, so I'm going to sub in y equals 2, and then I've got a tan of 4x. So 4 times 3 pi on 16. Okay, and then I can simplify that and solve for a. So 2 equals a tan. 4 times 3 pi is 12 pi, so we would have 12 pi on 16, or 3 pi on 4. Okay, 3 pi on 4 is, remember, in this quadrant, okay? And so it's got the same value as tan of pi on 4, but because it's in the second quadrant, the value of it is negative, okay? So the value of tan of 3 pi on 4 would be negative 1. Okay, so then to solve for a, we would just divide both sides by negative 1 to get a is equal to negative 2. Okay, now the question doesn't ask us to do this. We've actually done what it asked us for. It just said, what are the values of a and n? But if we then had to write the equation of this function, we would say that we've got this rule, y is equal to negative 2 tan of 4x. Okay, so that wraps up our lesson on the tangent function. Hopefully you're very comfortable with this function now. Remember, you're just using all of the same techniques that we've already used to solve any trigonometric equation and to sketch graphs and apply your transformations to this function. Okay guys, another little maths pun for you to start off this lesson. You know I love these. Stop sign. It's a good one. In today's lesson, we're going to be looking at the general solution of our trig equations. So these are going to be solutions of trig equations where we don't have a specified domain. So we're going to cover two things in this lesson. We're going to look at solving these equations without a calculator first, and then we're going to move to our CAS calculator and look at how we'd solve them using that. Okay, so what we're talking about here is we're talking about equations where we haven't specified a given domain. So with the other trig equations that we've solved up until now, we've said to you, find the solutions where x is between 0 and 2 pi or something like that. But this time there's no specified domain, okay? So because of the periodic nature of these functions, we have an infinite number of solutions. So what we need is a way to express that infinite number of solutions, and that's what we're going to be doing today. So for each of the functions, sine, cosine, tan, I'm going to take you through an actual example, and we're going to have a look at how we come up with sort of the general formula for these sort of general solutions that we're talking about here, okay? Now, believe it or not, tan is actually the easiest one, so we're going to have a look at that function first. So if we take a look here, I've got a graphical representation to the solution of the equation tan of x is equal to 1. So you can see here when I was talking about like infinite solutions, we've got a solution here, here, here. If we kept going, it's every time tan x intersects with the line y equals 1, right? We've got a number of solutions on this side and so on. Now, what we can think about is we can think about our reference angle or our first positive solution, right? And if we know our exact values, we know that the first instance when tan of x is equal to 1 is at pi on 4 radians. Okay, now my second solution, because the period of tan is pi, my second solution is going to be whatever my first solution was plus pi, right? And then it's going to be plus 2 pi to get to my next solution. And if I went this way, I would just be going, okay, I'm going to subtract pi to get to my next solution. So you can see here, like my solutions would be sort of 5 pi on 4, and then we would have 9 pi on 4 for my next one, and so on. So I'm always adding or subtracting pi to my reference angle. And that gives me this equation here. So the general solution of tan of x is equal to some value a is that x is equal to n times pi plus or minus, and then this is like your reference angle there, okay? The inverse tan of a. That's where we had our pi on 4. Now what this part here means is that I'm letting n be any integer value, okay? So if I look at my example that I just did, I had x is equal to pi on 4, then I had x is equal to pi plus pi on 4, then I had x is equal to 2 pi plus pi on 4. So you can see, like, this is the case where n is equal to 0, this is where n is equal to 1, this is where n is equal to 2, and I can do the same thing sort of on the negative side, okay? So that's where my general solution comes from. So if I was going to answer this question as a general solution, what I would say is x is equal to n pi plus or minus pi on 4 radians. And that's my general solution to this equation. Okay, we're going to do the same kind of thing, but this time we're going to look at the general solution for cosine, okay? So here what I've got for you is the graphical representation of cos of x is equal to a half. So we can see my first positive solution here. I know my reference angle there is going to be pi on 3, okay? All right, so that's my first solution, okay? So x, I'll start writing them down, is pi on 3. Okay, now if I look at this, my first negative solution here, this one I know because of the symmetry of the graph, that's just the negative of pi on 3. Now for every other solution, what I'm doing is, like if I want to get to this solution here, that's negative pi on 3 plus another 2 pi, okay? And to get to this solution here, I'm doing my pi on 3 plus 2 pi again, okay? And then that same thing keeps happening. I keep adding on multiples of 2 pi, okay? So what I start with here is I start with the negative and positive of that reference angle, and then I'm adding on multiples of 2 pi. Okay, so that's going to be my 2 pi n, and then n can be any integer value, 0, 1, 2, -1, -2, and so on. Okay, so that's my sort of general solution there. Typically, you'll see it written as 2n pi plus or minus the inverse cos of a. Okay, but that's exactly the same thing as I've written there. I wrote them the other way around just to show you how to derive that formula. Okay, so now we're going to have a look at the general solution of sine equations. Now this one's actually the trickiest one, so that's why I've left it until the end. But hopefully the way I explain it, you can understand where these equations come from. Okay, let's take a look first of all when we have sine of x is equal to √3/2. So we know from our exact values that that first sort of positive solution, our reference angle, is going to be pi/3. Okay, so what we have here is a solution at pi/3. Now my next solution, so I'll just start writing that down, x is equal to pi/3. Now my next solution is going to be right here. Okay, and we know because of symmetry and all of the trigonometry we've been doing so far that that solution is pi minus pi/3. And I'm going to leave it like that for now, pi minus pi/3. Okay, now because of the period of the sine graph, the period is 2 pi, my next solution over here is going to be 2 pi plus pi/3. I shouldn't say that's, but that's my next solution, 2 pi plus pi/3. Okay, and then my next solution here is this one here, and we can see that that's now 3 pi minus pi/3. Okay, and if I kept going, hopefully you can see a bit of a pattern starting here. What I would next get is 4 pi plus pi/3 or 5 pi minus pi/3, and so on and so on. Okay, so what we have here is for even multiples of pi, I'm adding on my reference angle. I'm adding that pi/3 on. But for odd values of pi, I'm taking away my reference angle. So we can write this one of two ways. The first way is we actually write it in two lines. So that's these first two here. What we say is I'm doing 2 pi n plus the reference angle, or 2n plus 1 pi, that accounts for my odd numbers, minus that reference angle. Okay, and so for this example here, the way we would write that is, so we would say x is equal to 2 pi n plus pi/3, or x is equal to 2n plus 1 pi minus pi/3. Okay, and where we have n being sort of any integer value. All right. The second way we can write this is quite clever. If we wanted to write it just in one line, what we do here is to account for, do you see how we go like plus pi/3, minus pi/3, plus pi/3, minus pi/3, and we go back and forth between it being positive and negative and positive and negative. What we can do to account for that is we put in this minus 1 to the power of n. Now if I do minus 1 to the power of 1, it's minus 1, right? And if I do minus 1 to the power of 2, it's positive 1. And if I do minus 1 to the power of 3, it's now negative 1 again, and so on. So adding that negative 1 to the power of n can account for me adding and subtracting that reference angle. Okay, so the second way, I'll just erase all this here, but the second way that I could write this, and it's your choice, you can write this either way, is I could just write it as n pi plus negative 1 to the power of n times the inverse sine of a, which in this example was pi/3. Okay, so we can also find the general solutions to trig equations with your calculator, and often this does come up as a multiple choice question on paper 2. So this is much faster, but you might need to do a little bit of rearranging, a little bit of algebra sometimes to answer the question correctly. So we'll see what that looks like with some of the worked examples. Okay, so when you're doing this, just make sure that your calculator is in radians. You're going to use your algebra solve function the way you normally would. So I've sort of given you a screenshot here of what the calculator input and output would look like. It will give it to you, instead of just writing n in here, it will write it down as like n1, n2, n3, depending on how many different questions you've solved. So we would just maybe write this as x equals 6n minus 1 pi over 3, or x equals 6n plus 1 pi over 3. Okay, so you're just replacing that n1, n2 that your calculator gives you with just a single n when you're writing it down on a paper. Okay, so the next thing we want to do is we want to find the general solution to this equation. So I'm just going to go into my menu and I'm going to add a calculator, menu, algebra, and solve. And then I'm going to just write in my equation like you normally would. Okay, so make sure you write your comma x in at the end. And then when you hit enter, you get something like this. So if we were just answering this on an exam paper, what we could write down is just those answers exactly how they are, but we'll replace our n1 with n. Now, this actually looks a little bit different to what we get if we use the equations that we were given without a calculator. So sometimes you might have to do a little bit of algebraic manipulation. And so I'll show you what something like that might look like, or we'll compare it to how you would get this answer if you weren't using a calculator. So if I was just solving this by hand, I would rearrange this equation to get sine of 3x is equal to root 3 on 2. Okay, so my reference angle there is pi on 3. So what I'm getting here is 3x is equal to 2n pi plus pi on 3, or 2n plus 1 pi minus pi on 3. Now, because in the brackets there we had 3x, we need to divide both of these answers by 3. So make sure you're dividing every single term by 3. Okay, so here we have 2n pi over 3 plus, this will become pi over 9, okay? Or we have x equals 2n plus 1 pi divided by 3 minus pi over 9. Okay, it's starting to look a little bit like what the calculator gave me. I can see a denominator of 9 there. What I'm going to do is I'm going to get a common denominator so I can add the fractions together. So I've got to multiply my first fraction by 3. So here I would get 6n pi plus pi over 9. And for my second one, I have, if I multiply this by 3, I have 3 times 2n plus 1 pi minus another pi over 9. Okay, now my first solution there, you can probably see if I factor out a pi, if I take pi out, and I'll write it the way it was in the calculator, okay, if I take pi out of those two terms, I end up with 6n plus 1 over 9. That's exactly what the calculator gave me. This one here, I've got to do a little bit more work to sort of convince myself that I'm doing the right algebra. So if I expand this bracket here, I get 6n pi plus 3 pi minus pi all over 9. Okay, this becomes 6n pi plus 2 pi over 9. And then I can factor out my pi, and I'll do it the way, it's a little bit funny the way the calculator gives it to you, but we can factor out a pi out of those two terms. I'll put our denominator here. And I can also factor out a 2. And then what I'm left with is 3n plus 1. And that's where you can see kind of the relationship between what you would do by hand and what the calculator gives you. Okay guys, so in summary, you've got the 3 trig equations, and then you've got the general solution for each of those. This could come up on paper 1, but I see it most of the time coming up as a multiple choice question in paper 2, which is helpful because you can have these in your bound reference, so you don't have to memorize them. But we never say never, okay? It could come up as a paper 1 question as well, so make sure you can also do these by hand. The next thing that we're going to look at is the last lesson in this chapter, and we're going to be looking at some applications of circular functions. Okay, the video you guys just watched was one of my favorite roller coaster rides at a place called Canada's Wonderland. Now, hopefully, or I think you've probably picked up by the time, I think we're on lesson 12 now, that I'm originally from Canada. That is one of the theme parks I used to go to all the time growing up, and that's like an amazing roller coaster, and it's just really one of those like up and down and up and down and up and down, but it's like really, really high and really, really steep. All that to say that something like a roller coaster could actually be modeled on a sine or a cosine function. So what we're going to look at in this lesson today are some applications of these circular functions that we've been looking at throughout this chapter. Okay, so we're really just going to be looking at different application type questions today, and we're going to be looking in particular at what we call the circular functions. So those are the sine and cosine functions. So far in this chapter, we've been looking at these in a very sort of mathematical way, but there are actually quite a lot of applications of circular functions, in the real world. So anything that has some sort of periodicity, so that means it repeats after a certain period, can be modeled using sine or cosine functions. So some examples, and these are examples that will probably come up for you in sort of an extended response type question, would be like tidal waves is one thing where they go out and they come back in, and the same thing sort of happens on a daily basis. Or a Ferris wheel, or anything with any sort of like rotation, can be modeled on a sine or cosine function. Average sort of daily or monthly temperatures, those are cyclical in nature. So again, can be modeled using sine or cosine. Harmonic motion, sound waves, anything like that. So these are all sort of the applications that you might see commonly in your exam questions, but they are actually like real world examples. Your functions might be a little bit simplified, but they are useful. So since we just watched a video of a roller coaster, I thought we would start with that. So here we've got a function, and it describes the path of a roller coaster at an amusement park. Okay, so we have h is the height above the ground in meters, and x would be the distance along the ground in meters. Okay, and here we have x going between 0 and 100 meters. Okay, so the first thing we're going to do is we're going to state the period and the amplitude of the roller coaster. Okay, so nothing tricky about this. This is exactly what we've been doing with our functions all along. Okay, so the period, remember, is 2 pi on n. In this case, n is 2 pi over 100, right? It's the coefficient of x. So we have 2 pi divided by 2 pi over 100. Okay, so what happens here is our 2 pi's will cancel out. That becomes 1 divided by 1 over 100, which is actually 100. Okay, so the period of our curve is 100. The next thing we want to do is find the amplitude. So remember, the amplitude is the absolute value of A. Okay, so the amplitude in this case is just 5. Okay, and you could state, because we're talking about meters here, that both of these would be in meters. Okay, so part B of this roller coaster question would now be to sketch this graph. So sketch the graph of h against x. Okay, I'm just going to write down again. We had an amplitude of 5. We had a period of 100. And we can also look at what our range would be, okay? So because our amplitude is 5, normally we would go between -5 and 5, but we've actually got this shift up by 5 as well. So my range now is going to be between 0 and 10. Okay, so let's start to sketch this. We'll just do it like really roughly, but we would start at when x is equal to 0. Okay, we're going to have, well, we can put in x is equal to 0 and work this out. But we end up with -5 cos of this whole thing becomes 0, right? 2 pi times 0 over 100 is just 0 plus 5. Okay, cos of 0 is 1, so we end up with -5 times 1 plus 5, which is 0. So here I can see my starting point is 0, 0, and that makes sense because we're actually dealing with a reflection. We've got that -5, we've got a reflection of the cosine curve. Okay, now my period is 100, so between 1 and 100, I'm going to have a full cycle of this like reflected cosine graph. So I'm going to have something that's like upside down cosine graph. And then what else is important to note on here? If my range is between 0 and 10, then I'm going to have a maximum point here at 10. Okay, and you don't have to state this, but if we just like sort of investigate it even further, you should be able to, because of the symmetry of the cosine curve, you should be able to recognize that that maximum value of that curve there then is at the point 50, 10. Okay, so there's a nice sketch of our graph. Okay, so now we have a new part sort of added on to this question. Okay, so we had our original roller coaster, and then our engineers have designed a new roller coaster for the park that's more thrilling, a more thrilling experience. Okay, so the graph of the new roller coaster is the one that you see in front of you on the screen. Okay, so using this graph, we now want to find a new trig function that describes the path of this new roller coaster. Okay, so let's think about the key features of this graph that we can see. So looking at it here, it's very clear that my period is 50, right? You've got one cycle of the curve at 50. So my period is 50, and this is going to allow me to calculate the value of b in this equation here, but that coefficient of x, okay, is dependent on the period. So remember the period is 2 pi divided by b in this case. So we have 50 equals 2 pi divided by b, and that gives me b equals 2 pi or 50, or pi over 25. Okay, so that's my b. Now let's take a look at a. Remember, a is dealing with the amplitude. So the amplitude is half the distance between the minimum and the maximum of the graph. So we can see the minimum is 0, the maximum is 20, so the amplitude is 10. But that's not our a value because this is a reflection of the cosine curve, okay? Normally, the cosine curve would start, say, up here, and we would draw it that way, okay? But this graph is upside down, so that tells us that the value of a is negative, okay? So here we know a is equal to negative 10. Okay, so we've got BA. What's happening with D here? That's the other variable that we need to work out. Now, D is my translation, either up or down, okay? Now, normally, the sort of center line of my, of a circular function or of sine or cos is around the x-axis, but you can see now that that's been shifted up by 10. Okay, so that means that this graph has been translated vertically or in the positive direction of the y-axis by 10 units, which gives me a d value of 10. Okay, so my new equation would be h is equal to negative 10 cos of pi x over 25 plus 10. Okay, and if you're working on a calculator paper, you could always check your answer here by actually putting that equation into your calculator and making sure you have the correct graph. Okay, so our second example here is dealing with temperature across time. So we've got a 24-hour time interval. The daily temperature in a particular city is given by this equation, okay? 25 minus 4 times the cos of pi times t on 12. And then we've got t being between 0 and 24, okay? Little t is the time in hours from midnight, and big T, we're told, is the temperature, okay? So the first thing we want to do is state the maximum temperature and then the time that this occurs. So I'm going to show you how you would do this both with and without your calculator. If we want to find the maximum temperature, we want to think about, first of all, what is the maximum and minimum value that cosine could be, okay? The maximum value that cos of an angle is 1. And the minimum is -1. And that's going to help us with a lot of these questions. Okay, so what that tells us is that if we looked at, like, say, the minimum value of cosine and we subbed it into our equation, we'd have 25 minus 4 times -1, which would give us a temperature of 29 degrees. If I put in the maximum value of cosine, the maximum value of cosine is 1. That gives me 21. So what that's telling me is my maximum temperature is 29 degrees and my minimum temperature is 21 degrees. But let's take a look at the graph of the function to see what that looks like. Okay, so I'm just in my graph function here, and the first thing I'm going to do is I'm going to put in the equation. So make sure you're using the variable x instead of t when you're putting it into your CAS calculator. Okay, when you first hit enter, don't be alarmed if you don't see anything. It just means that you need to change the view of the screen here. Now I can see here that I'm going to have a temperature. I have T, my little t, which is my x-axis, between 0 and 24 degrees. So the first thing I'm going to do is I'm going to change my my axes to kind of just show that area. So if I double click on that -10, I can change that to 0. Okay, and then that can go up to 24. And I still can't see anything, but that's because my temperatures, you can see maybe by the 25 in that graph, first of all, that's a vertical shift up 25. So I'm going to have to see a higher sort of portion of my graph here. So let's just change this to, I've got 25 and then an amplitude of 4. So like that's where I'm getting my maximum value, you can see now, of 29. So I'll just make it show up to 30, and then here we get a nice sort of image of our graph. Okay. All right, so I wanted to find the maximum temperature, so I'm just finding the maximum of that graph. So I can go into my menu and I can do number 6, my analyze graph, and then I can find my maximum, which is number 3. Okay, so I can see where the maximum is, so I'll set my lower and upper bound, and I can see here that I have a maximum at the point 1229. So interpreting it within this question, the question told me that little t is the time in hours from midnight. Okay, so the time in hours from midnight would be 12 hours from midnight, so it would be at 12 p.m. and then the maximum temperature there is 29 degrees. Okay, so 29 degrees at 12 p.m. would be fully answering that question there. Okay, so part B of this question asks you to state the period of the function. So we can do this without our calculators. We're just having a look. We can see the coefficient of t is pi on 12. So the period would be 2 pi divided by pi on 12. Okay, the pi's will cancel out. That's 2 divided by 1/12, or 2 times 12, which is 24. Okay, and that's all we need to do for that. And that kind of makes sense there based on the graph that we saw before when we were looking at the function. The period did look like it was going between 0 and 24. And within this context, we're looking at the temperature, the daily temperature, so like 24 hours it does seem to be like a normal period for this kind of function. Okay, so part C of this question asks us to find the smallest value of t for which t is equal to 23 degrees. So in order to do this, we're just going to graph the line y equals 23 degrees. So I'll press tab on my graph to get another function up, and I'm just going to put in 23. Okay, and where those two graphs intersect is where we're going to find our answer. So you can see the graph intersects in 2 places, but we were asked to find the smallest value of t, so we're just going to look at this first intersection point. So if we go into our menu, Analyze Graph, we're going to now look at the intersection, which is number 4. Okay, and we're going to do our lower and upper bound around this point here, which is our intersection point. So you can see that it intersects at 423. So the answer to that question, the smallest value for which t is equal to 23 would be 4. Okay, part D of this question says, for how many hours during that 24-hour time interval is t greater than or equal to 23? So now we're looking for the part of the curve that is above 23. So we need to find our second intersection point here first. So if I go to menu and then Analyze Graph and then intersection, I now want to find that second intersection point. And I'll just move that a bit so we can see it. So we can see that the second intersection point is at 20 and 23. Okay, so the temperature is above 23 degrees between the times when t equals 4 and t equals 20. Okay, so the difference between those two would be 16. So the answer to that question would be 16 hours. Okay, guys, so here's a summary of what we've done so far. So I've just restated there the properties of sine and cosine for you. These come in really handy when you're answering your application questions. And then I've got a few hints for you, things to take note of or make sure of when you're answering these questions. So first off is always make sure your calculator is in radians. If you can, sketch the graph or draw it on or use your calculator to give you an image of the graph. Make sure you check to see if the graph is reflected. Often in these, you've seen with cosine, it is often a reflection. So make sure you take note of that. Remember that sine and cosine both have a minimum and maximum value of 1 or -1. So you could just sub that in when you're trying to find a minimum or maximum of an entire function. The period is always going to be the length of time for one cycle or one rotation. And always make sure you check the domain. It's very likely that it's going to be restricted to fit within whatever the context of the problem is. Okay, guys, that is it for our trigonometry chapter. The next thing that you've got to do is test yourself. So if you're ready for some exam questions, you can go into the chapter checks. Good luck.